simple system.
Okay, thank you very much. I would like to thank Katie Karate for organizing this workshop. It's a very nice idea. Thank you very much for opportunity to make a talk here. And my talk is based on joint recent paper with Andrey Zotov, with just the same title, and we have a kind of continuation of this paper, also recent, which is devoted to Srednik operators and Nazarov's-Kleinin construction. And this is maybe I will talk about a little in the end of the talk. Okay, here's the plan of the talk. I will start from some basic facts, just to recall and to introduce notations, then proceed to main statement about determinant representation of generating function of Hamiltonians, and then I discuss some classical counterpart of this story related to factorized Lax operators, Manakov triple, and so on. And in the end, I come back to quantum problem and discuss some open questions and how quantization can be realized. Okay, let me begin with a definition of a widely known integrable system of Calogero-Sutherland type. It is a model of interacting particle on a complex plane. Here U is a potential and mu is a coupling constant. And the model is integrable for the following potentials. And we deal with elliptic case. It is a Ruijsenaars pi function, and its trigonometric analog is inverse sine, and the inverse squared argument is a rational analog. We use standard definition of theta function. It is the one which has 0 at 0, and it is odd. And here we have some simple expression in the trigonometric limit, so it behaves up to some common factor, it behaves like sine. And it is given here also. So, let me recall that in classical mechanics, we deal, when discussing Lax representations and so on, we deal with a set of functions, quite simple functions constructed by means of theta function. And the main one is the phi function, which I call Kronecker function, following Andrey definition. This is it is this ratio of theta functions which turns in trigonometric limit to a sum of cotangents and to sum of inverse arguments in the rational case. The function is has very simple properties. It has simple pole at 0 with the reciprocal equal to 1. It has the quasi-periodic behavior on the lattice of periods, like given here. And the main property is that it satisfies the following addition formula, which may be viewed as genus 1 phi identity. Well, in fact, it is just a written Riemann identities for theta functions. And this phi identity or addition formula is easily can be easily understood in the rational case. In the rational case, for example, we have a very simple addition formula for inverse square argument function. We just write down obvious identity divided by the product of variables and have the addition formula. And the one for the function phi in rational case is just a little bit more complicated because it depends on two variables, but it's very much the same. And what we are discussing and what we call the Phi identity is its analog for elliptic case. And this formula underlies most of constructions in elliptic integrable systems, including classical Lax pairs, R-matrix structures, and quantum R matrices, Yang-Baxter equations, scaling algebras, and so on. And here, let me just recall, also for mostly for notations, that the what is.
Excuse me, Andrey, is the QQ tilde system is one of them in a XYZ case? Can you put the next slide back? So is it looks like the QQ is the one with the phi, like the phi identity.
Yes, the phi identity. So what is the question?
So is it an example of the QQ tilde equation for XYZ spin chain or not? Or is it different? It does look like, QQ.
QQ tilde, do you mean a Baxter equation?
Yeah.
Okay. All these type equations are based on the addition formula. Just it can be not obviously, but in fact it is, of course.
Okay.
It is. In classical mechanics, the Calogero-Moser model is described by the pair of matrices called Lax matrices with spectral parameter, which were introduced by Krichiver. And here's example of explicit formula on this topic, and we see that the Lax matrix is exactly constructed by means of this phi function, and the M matrix or company matrix in the Lax equation is a derivative of this phi function. In fact, I don't need too much details here. I just want to show that the models we're going to discuss are described by the Lax pairs, which are constructed by means of this function phi. And another example important for us is the Ruijsenaars-Snyder model. It is a deformation of Calogero-Moser model to relativistic case. Here, eta is a coupling constant, and E1 is a logarithmic derivative. Here, this is E1. It's a logarithmic derivative of theta function. Or you may think of it as Weierstrass zeta function. It's also true. And the Lax matrix is again a phi function and some multiplied by again the ratio of theta functions. So the idea I just wanted to recall and to say it again is that we always deal with some addition formula, and when we talk about Lax representations, we talk about this phi function, and most of structures are constructed through this function and its main property. And as you could see, when we wrote down these functions, they were given in rational, trigonometric, and elliptic cases. So we have three types of models. And if we look at dependence on momenta, then in Calogero-Moser model case, we have a linear dependence on momenta in the Lax matrix, and exponential or trigonometric for the Ruijsenaars-Snyder model. And the natural question exists, what about elliptic dependence on momenta? Can we construct it somehow? And can we wait for existence of these type models? And here I should say that the origin of many body systems with elliptic dependence on momenta came from the so-called Ruijsenaars duality, or action. It is also called action angle duality or PQ duality. It is, in fact, it interchanges action variables and coordinates into models. And here I give just to recall a simple example which shows that the rational Calogero-Moser model is self-dual. So we have in this case the Lux matrix of this form without spectral parameter, which we tend to infinity, for example. Then it satisfies this matrix equation, or this one equation. It is just the same. These are just in. It is this equation, but written in components. We can conjugate it by matrix of eigenvectors to diagonalize the Lux and bring it to some lambda, which is diagonal, and then these diagonal variables are action variables, and Q is mapped to some L tilde, and it can be easily shown that L tilde satisfies a very similar matrix equation and can be solved just in approximately the same form. And this construction shows that the Calogero-Moser model is what is called self-dual with respect to this Ruijsenaars duality. But if you consider some, yes, and this matrix equation is known as moment map equation in group theoretical approach. And if you consider, for example, some slightly more complicated case when one of variable is group valued, then the moment map equation takes this form, and we can solve it with respect to A or G, and solving it with respect to A with diagonal G, we get the trigonometric Calogero-Moser model, or solving it vice versa with respect to J with diagonal A, we get the rational Ruijsenaars model. And these models are again dual in the same sense. And then then we can await that something like this can be done for elliptic model, but exactly this skin doesn't work because in elliptic case we have Lux representation with spectral parameter, and we don't have finite dimensional reduction procedure. But so in some way it can be done. However, because we understand that the two models are related by anti-canonical map, and using this definition, Mironov, Morozov, and many other co-authors found that this model can be constructed. I mean, the model dual to elliptic Calogero or elliptic Ruijsenaars model, and a self-dual elliptic model also exists, which has elliptic dependence on both momenta and coordinates. And here is a famous table which shows relations of this PQ duality between different models. In horizontal line, we show the type of coordinate dependence, and on vertical line we show the type of momentum dependence. And as we saw, the rational Calogero model is self-dual, and as we just briefly told, the trigonometric Calogero model is dual to rational Ruijsenaars. The trigonometric Ruijsenaars model is self-dual, and in this corner we have models with elliptic dependence on relative dependence on coordinate and on momenta. And so these three models are of our interest, but unfortunately we don't know their description in algebraic terms. We don't know Lax representations, we don't know aromatic structures. For this reason, we use another definition of double elliptic system, which was suggested by Karateev and Shakirov. And I hope to clarify how these two descriptions are related. It's a very interesting question, but now I just should make some kind of a jump in the logic, because previously I told about this picture, which was given, which was based on PQ duality, and now I'm talking about different definition. And in this different definition, we're going to use a slightly different, slightly modified theta function. It is just approximately the same, but it differs by some common multiple, some exponent.
Andrey, may I add a comment? Yeah, so indeed, as you said, it's still an ongoing problem whether the DEL, in our paper with Shamil and this DEL model that you guys were talking about, like in ITAB before, same thing, but with everything else in the table, we have an agreement, right? So like the Hamiltonians, say, for example, for elliptic RAS model, they are, those which you get from cyberquoting geometry are the same as you would get.
Yes, yes, this is
sort of like the sort of the problem, like it's not clear still only in the bottom right corner.
Okay,
so
okay.
Complicated system.
Yeah, your Hamiltonians seem to be not self-dual, and maybe the ITAP ones also not self-dual. This is also not very clear.
I had an email exchange with them like yesterday, but somehow none of them are here. Okay, but maybe they'll join in later during the work.
Peter says that there is the same table, but without arrows, meaning PQ duality. And
I mean, I'm just saying that there's the same table, but like on every cell, you can put the cyberquoting geometry, like the gauge theory whose cyberquoting curve provides the spectral curve. So this is known for all models except the DEL. Although there's a DEL formulation by Harry that Braden, Hollywood, and Wafa and others, but like it's not clear whether that model is the same as the PQ self-dual model by Mironov.
Okay. So, and let me recall the definition by Karateev Shakirov. Their definition is as follows. We have a set of operators ON, which are defined by this generating function. Here we have this definition is very similar to definition of a product of theta function. Just it looks to be complicated for the first look, but if you put n equal to 1, then you reproduce just theta function of this expression. Here's a shift operator multiplied by spectral parameter and nothing more. And here it is a ratio of theta functions of Vandermonde type. And here is a weight, and this weight is very similar to the one standing in the definition of theta function. So by decomposing this expression, we have a set of operators, but the statement is very non-trivial. The statement is that you should consider this combination, and only these combinations are commuting Hamiltonian, not the ON operators, but only these expressions. And as far as I know, this statement is still not proved yet, and so it should be regarded as a hypothesis which was verified using computer. And yes, just I should say a little more about notations. Here now we use X for positions of particles, and this is why, and they are exponents of the previous position, so we have multiplicative notations. This is why the shift operators are written in this form, and the T is exponent of coupling constant, and Q is exponent of Planck constant, and omega is the second modular parameter. So we have tau standing here in these theta functions, and tau tilde standing in this omega. Okay, and my talk is based on the assumption that this is true, that these Hamiltonians indeed compute. And my statement is the following. Let us slightly modify the definition of generating function of O operators. We insert this ratio of theta functions, and we insert dependence on additional spectral parameter. So we had only lambda, but now we have lambda and z. And here the sum, in each term in the sum, the theta function is shifted. Then we can write down this expression, and
Andrey, can I just ask, in the sort of Braden Hollywood picture that followed on from, I guess, Doka, Fong, etc., those are the same parameters, is that right?
Sorry, can you repeat the question?
In my spectral curve, I would have had a Z and a K, I guess, a Z and a lambda, and it was got by such a shift. So I'm just wondering, is there a connect? Should I be looking at this and seeing the quantum variant of the spectral curve that Hollywood and I wrote down?
Z and lambda indeed play the role of a pair of spectral parameters in the elliptic Ruijsenaars-Schneider model, but in some not straightforward way. I will show a little later. Okay.
Okay.
Now my statement is as follows. So that consider this generating function. Then it can be presented as a determinant of this sum, of the averaged sum of Ruijsenaars-Schneider quantum lux matrices with shifted Planck constant and complete constant. So you see that in this sum, each term has different values of Planck constant and coupling constant. And we consider the averaging like in the definition of theta function, the averaging over z, and then we compute the determinant, make the normal ordering, and then the statement is that this expression is equal to O, which is used for constructing Hamiltonians.
And eta, sorry, and eta, there was no eta in Karateev-Shakirov, or was there?
Eta is related to T.
Yeah.
T is the exponent of eta.
And T was?
T standing here. It's a shift in theta function.
But what is this meaning? Is it like a B in Ruijsenaars is like the
coupling constant in terms of gauge theory? It's the mass of the two star.
It's a mass. Yeah. Okay.
Okay, and let me just briefly say the idea of the proof. In fact it's very straightforward. It's you should just write down the determinant by its definition, and then write down matrix elements which are given explicitly according to this formula, and then see that the all this expression is a sum of determinants. It happens because you may combine you may combine matrix from different columns depending on different values of coupling constant and Planck constant. So you may combine this expression into some of such determinants, and this is in fact the end of the proof. You then should just substitute the elliptic Cauchy determinant formula. The elliptic Cauchy matrix is exactly the matrix constructed by means of phi function depending on two sets of variables, and the formula for elliptic determinant is widely known, and you just may straightforwardly calculate the determinant of this expression and then substitute it into the sum I just showed, and see explicitly that it works. So I understand that it is quite difficult to see details of a proof or calculations from the screen, but I want to say that you may find it in our paper, but I want to say that the idea is not complicated. It's just a straightforward verification, and the only thing which we use here is a formula for elliptic determinant.
Sorry, can you show the statement again before the proof? So you're saying that before the proof, yeah. So that yes. The del L, or you define the.
So you see, we began with this definition, yeah. Then yep. We modified it in this way.
Yep.
And we now say that this modified definition is a determinant. Is a determinant of this expression.
This expression.
And this expression means that you roughly speaking, you consider a theta function of Ruijsenaars-Snyder-Lux operator.
Yeah. Well, I was thinking about the determinants. Like if you take the determinants of Ruijsenaars, then it's like a conserved quantity. The determinant of Lx, it's like a Hamiltonian, or. But then it's straightforward that everything would work out. But now it's not straightforward because it's some kind of resumming of Lx of another and then taking the determinant. That's why it's not obvious. Why is this?
It's absolutely not obvious, because each term in this expression is a Lux matrix which depends on different Planck constant and coupling constant.
Yeah. So, yeah, and then each matrix Lux element is not any kind of conserved quantity. It's just something.
No. Yeah. So, okay, but now we need the next step. Recall that the definition of O operators is an intermediate step, and in order to have Hamiltonians, we need to consider this expression. And what I want to say is that instead of this set of operators, we can consider a different set. And this different set is as follows. It is given here. So instead of O0 inverse, we might put here O dependent O with substituted lambda equal to 1 inverse. And if this set is commutative, then this set of operators is also commutative. And it's a simple algebraic exercise. Just to prove it, you need to consider ratio of two Hamiltonians by Shakirov-Karateev, and this ratio is equal to the ratio of O operators, and then you just need to multiply it by some other inverse O's and sum up over some indices, and it's a simple exercise, I should say. Everyone can do it. I just don't want to stop at this place. The statement is as follows. So if we have this set of commuting operators, then this set of operators is also commutative. And why do we need it? On one hand, this new quantity compared to O0 is hard to inverse because its series expansion starts not with 1. But on the other hand, we have a determinant representation for this expression O of 1. Then the Hamiltonians, the generating function of Hamiltonians, requires the form of a product of of normal orderings of some determinants. This expression was written for O of lambda, and this expression is O of 1 when lambda is substituted to be equal to 1, and we put inverse power here also. But we cannot unify them because the product of normal orderings is not a normally ordered product. However, in the classical case, we may remove the normal orderings, and then the product of determinants become the determinant of a product, like it's given here. And this is just the main step of our construction, which leads to the following statement, that in fact we deal, at least in classical case, we deal with the following expression, and its determinant is generating function of classical Hamiltonians. So we should take the Ruijsenaars-Snyder-Lux matrix, consider the following averaging like in the theta function definition, then construct the following expression, and its determinant is the generating function of commuting Hamiltonians. This is the main result, and this is the main rule I want to discuss. And this matrix, this L, can be called a spectral matrix. So it depends on two spectral parameters. Recall that in the usual case, when we say in any integrable system, if we have a Lax matrix L small depending on Z, on spectral parameter, we usually construct its characteristic determinant and call it spectral curve. But now we cannot. We have just some matrix which is not represented in this way, but it depends on both variables, and one can verify that in the limit when omega goes to 0, one has for this L the following expression. It is 1 minus lambda multiplied by L Ruijsenaars-Snyder, and then the ratio of such L's, the ratio which is through L matrix, the spectral matrix, is represented as given here. So it's I'm answering question how it is related to spectral curve. The relation is not straightforward, so it is indeed, as we can see, you may of course consider this function of the Lax matrix for the Ruijsenaars-Snyder model, and it is again the Lax matrix of the Ruijsenaars-Snyder model, but written in some complicated way. So however it is directly related to spectral curve of the Ruijsenaars-Snyder model, and you can so you can perform some change of variables which maps the usual description to this one. And in fact, we can hope that our matrix, depending on two variables, is we just don't know how, but we can somehow represent it as a determinant of possibly infinite matrix with some special change of variables where u depends on both z and lambda, and zeta depending on both z and lambda. And this L is an infinite matrix. But we don't know these change of variables, unfortunately, and so we should deal with this expression.
Sorry, a quick question.
Mm-hmm.
About the parameters. It's maybe not exactly like in the last paper, like Zinkevich, Mironov, and Morozov, right? They also make some comments about your Hamiltonians, and they say like somewhere the dependence on the parameter drops somewhere, or is it not here? Do you know what I'm talking about?
Say it again.
They say that there's some identities, and then the dependence on the parameter drops somehow, like maybe in your formulation.
You mean globally, the only place in the paper when they talk about it, it's like inside the identities for wave functions. There's a complicated the statement that the wave functions of the system which are known are actually the functions of these operators relies on some complicated theta function identities.
Yeah, and so then in this computation the dependence drops. Yeah, okay. When you consider wave functions. Okay.
Probably, I just don't know what exactly you asked.
Yes, I think you're right. Yeah, they were talking about acting on wave functions, and then you need to drop some spectral dependence there.
Mm-hmm.
Yes.
Okay.
Okay.
So now, and what we know is that this expression generates a commuting set of Hamiltonians through its determinant, but it should be stressed that the eigenvalues or traces of powers of these matrices are not conserved quantities. And this situation is also widely known in integrable systems. So in this case, you don't have Lux representation, but you have Manakov representation. So instead of only this part, you have some additional term where B has trace 0, and then in this case, from this equation, it easily follows that determinant of this matrix generates conserved quantities. Likewise, in the usual case, you similarly show that the traces of powers of this matrix generates the set of conserved quantities. And so what we conclude that we can come to Manakov triple description of the Dell model. And now I have about 10 minutes. Yes. Let me briefly talk about some more properties of these matrices. I need to recall the phenomenon which is known as IRF vertex relation, the relation between dynamical and non-dynamical R matrices, and quantum models related to dynamical and non-dynamical R matrices. In the simplest case, not in the simplest, yes, but it's exactly the elliptic case. Okay, so it can be viewed as a kind of quantum gauge transformation acting on the matrices, and for example, the quantum Felder's R matrix is a dynamical one. It depends on Q's, And on the other side of relation, we have the Bellevin-Sar matrix, which is non-dynamical. It is the one which describes XYZ spin chains and the extension to Lie group. The R matrices are related in the following way, but and the relation is given in terms of a single matrix J, which is known as intertwining matrix. It was introduced in n equals 2 case by Baxter and then studied by Jimbo, Muir, and many other people. And the matrix is explicitly given here, and it has trigonometric and rational analogues, and I will show it. And what is important for our topic is that the Lax matrix of Ruijsenaars-Schneider model can be written in terms of this matrix, intertwining matrix. So again, J is this some explicit matrix depending on positions of particles. Then the quantum Lax operators of the Lax operator of the Ruijsenaars-Schneider model can be written in the following form. This statement was mentioned by Koji Hasegawa, and we use it here widely. The classical version of the statement is as follows. So that we have this very compact and nice form for a matrix. And for example, in non-relativistic limit, when eta goes to 0, we reproduce the Calogero-Mozart model in the following way, where pi is a diagonal matrix of momenta, and all non-trivial part of the Lax matrix is converted into pure gauge along the spectral parameter, and the gauge group element standing here is exactly the intertwining matrix. Okay, so keeping this in mind, we may rewrite our answer using this intertwining matrix. We want to make one more step and to write for right expression which unifies both Calogero and Ruijsenaars models in the following way. Introduce this J large, which is this intertwining matrix multiplied by some exponent of momenta and with linear dependence here on in Z. Then the Calogero Lax matrix is obtained from this formula by substituting f to be a linear function. And the Ruijsenaars-Schneider Lax matrix is reproduced by this formula by substituting here the exponent function. And it was my wish to some years ago to find the answer how can we find elliptic analog for this function phi, and now we come to answer to our question that there is a natural candidate for this function phi, which we should substitute here to obtain an integrable system. So here I just recall, I think we may skip it. I recall explicit expressions for the intertwining matrices in trigonometric and rational cases. They are just a kind of van der Monde matrices with some jumps at last rows if spectral parameter exists, and without any jumps in the cases without spectral parameter. But it's just I want to say that all these matrices in all the cases with spectral parameter and without spectral parameter in rational and trigonometric cases are explicitly known. And now the answer for the function phi, which should be substituted into that formula in order to have again integrable system and to reproduce our answer for the L matrix of Manakov type, is just a phi function. It's just a ratio theta function. We began with a phi function, which was a Kronecker function underlying Ruijsenaars ansatz for the Lux matrices and so on. And we turned back to this phi function in the end of the story, but now it's phi function depending on the dual modular parameter, and we use it in the following way. I just showed the answer. In order to have expression for the Manakov cell matrix, we need to use the phi function in the following way. We consider the following expression where the theta function of dual modular parameter is considered as operator acting on intertwining matrix. And here is a combination, and this combination in trigonometric and momenta limit just turns back to this definition, to this formula, to the Ruijsenaars factorized formula. And here we presented its elliptic analog given by phi function. And in this way we come to the same table as Mironov Morozov suggested, but we just here we describe by this table we mean the following. We don't discuss dualities here, but we have a concrete recipe for construction of L operator for each model. For the known models, we have explicit form of flux operators in Calogero case and in Ruijsenaars case. And for double elliptic type model, we have not the Lux representation, but Manakov representation. But all of them are written in a very similar way when represented in factorized form. The only thing you should know, you should choose some intertwining matrix depending on coordinates, and you should choose rational trigonometric or elliptic phi function. Then you substitute it to this formula and obtain expression for operator. So I have, I think I have no time to discuss.
Yeah, that's a couple of minutes. Yeah.
Okay, to discuss quantization, but let me say a few words. The quantization can be performed in two ways. The first way is just to follow Ruijsenaars' construction. The Ruijsenaars who mentioned this relation, let me just show it again, that the Ruijsenaars-Schneider quantum Lux operator is represented in this form, use it as follows. He conjugated this expression by J and found out and proved that this conjugation provides Sklenin type Lux operator, and the Sklenin type Lux operator is a good object. It satisfies RTT relations with vertex type R matrix, and it's quite easy to deal with. And through these steps, he interpreted it as quantization of Ruijsenaars-Schneider model. And we can perform the same calculation here. We may look at our L matrix for the Dell model, also conjugated, and then instead of theta function of Ruijsenaars-Snyder-Lux matrices, we come to theta function of Sklenian type Lux matrices, and so it's the first attempt of quantization, and we can, moreover, we can come to concrete realization, to concrete representation, to vector, for example, to vector representation of quantum R matrices of Belayan type, Baxter-Belayan type, and then we come to the objects of this type, where again matrix element of our matrices are averaged as in definition of theta functions, but we don't know in fact what is the nature of this object. For each term in this sum, we know that it satisfies Yang-Baxter equation with concretely this Planck constant. But for this sum, we don't know equation which is which this expression may satisfy, and this is an interesting question. Another possibility to describe the quantum Ruijsenaars-Snyder model is to consider Cherednik operators. Consider the coordinate trigonometric limit of this expression. So instead of this, the ratio of theta functions, we put here the ratio of these differences, which are in fact similar to the ratio of sines. And in this case, in this case, we come to this expression, yes, for generating function of all operators. And this D is also, and when omega goes to 0, so in the limit to Ruijsenaars-Snyder model, to trigonometric Ruijsenaars-Snyder model, this D is very good object. It is represented as a ratio of determinants, and gamma here are shift operators, I did say, but I have no time in fact. And this, just a few words. And this expression, the generating function of Hamiltonians, appears from Cherednik's operators. The Cherednik operators are the following expressions of R operators, or which can be called R matrices or R operators. Here, these R operators are operators depending on the operator which permutes, explicitly permutes coordinates of position, coordinates of particles, positions of particles. And the statement that McDonald-Ruijsenaars operators commute follows then from two facts. The first important fact that the Cherednik operators commute, and the second fact that this Dn, this generating function, is obtained from Cherednik operators by considering it on the space of symmetric function. So this relation follows. And in the last paper with Andrey Zotov, we tried to extend this definition in order to construct double elliptic version for Cherednik operators in the same way, so in the natural way as it was performed, for example, for Lux operators. And we found that these operators do not commute with each other. However, the statement that this product been restricted to the space of symmetric functions indeed reproduces the generating function of commuting operators, of all operators, and the ratio of this expression provides generating function of commuting operators. And this can be used for constructing Lagrangian limit through quite tricky and complicated construction by Nazarov and Sklenian, but it appears that this can be extended to the double-elliptic case. And the last page, I just to say in just 2 words that we discussed. It's just intriguing question for me that we discussed the dualities between many body systems, and as is widely known that there is a set of similar dualities between Gaden type models and spin chains, for example, and it is known also in different ways, like JLN duality due to Tarasov, Marchenko, Mukhin, or spectral duality in our papers, or some other formulation, dynamical equations, if we talk about Knyzhnik's homological equations. So this phenomenon is widely known, and in these phenomena, for example, the rational Gaden model is self-dual. Trigonometric Gaden model is dual to XXX spin chain, and so on. And what we yes, and what we want to what we need is to reproduce the del counterpart of spin chains. It was not defined yet, and it is very interesting to define it. Okay, thank you very much.
Great, thanks a lot.
I should stop here.
A very nice talk. Yeah, so unfortunately we're running short on time, so I do think we need to find time for discussions. So I'll email you guys about extra time for a questions and answers session. But now, if there's any quick question, we can you can go ahead and ask. So if there are any quick question.
A quick question.
Mm-hmm.
So there's you're talking about the spin chains. There's four multiplet version. Does it fall into this category when they have like 2 hypermultiplets and fundamental representation from gauge theory? Is it a spin chain?
I think it's a question to you. You know,
I think
Zybek-Witten description better than me.
That would be the spin chain, but in the standard kind of the gauge, the kind of Zybek-Witten geometry, right? It's not on this table.
But you have a spectral curve, which is the spectral, the quantum or classical spectral curve. Does it correspond to spin chain? It's like from Yegor's and your guys, you were doing it. I'm just saying because like from four hypermultiplets, you have a limit to Calogero. So you should in 4D. So maybe there's some help like relating, but yeah, I don't know. This I need to know what kind of spin chains there. But like from gauge theory, if you have four fundamental hypermultiplets, you can have a limit to a joint matter, which is elliptic Calogero. And then going to del means that you want to look maybe at like 6D theory or something. So yeah.
No, as for me, I'm not ready to discuss the Zybek-Witten counterpart of the story. Not yet.
But it should work. The limits, they usually work, right? The limits that you have in Zybek-Witten, they're in terms of the limits are in terms of cutoffs and masses. So the limits should work, I think, in theory.
Guys, let's.
Yes, of course they should work.
Discussion. Yeah. We need to move on to Simon's talk.
Yep.
Okay.
Yep.
So
thank you.
Thank you very much. Great. So now next talk will be by Simon Ruijsenaars. So Simon, I just made you the co-host. You should be able to share a screen.
Okay, let me unmute my.
Also, while you're doing this, may I ask you what you did to log in? So Slava Spiridonov is sending me emails. He cannot log in. You said you made a trick or something. You had problems with logging, and now you managed to get in.
Yeah, I used a browser instead. That worked.
Okay, so I'm going to just do not the Zoom app, but the browser. Okay, I I see. Great. I'm going to tell Slava to do that. Because other folks who have 20 people in, so did anybody else had problems with login? With the login into the conference?
I did, Peter, but I eventually got in.
Are you using the app, Harry, or the browser?
I came in via a browser.
I see. Okay, good. Thank you very much. Yes, I'm going to tell Slava to. Okay, great. Sure. So Simon, whenever you're ready.
Yeah, I'm trying to share, but there's some problem with the privacy. What am I supposed to do here? I get this message that I should do what? Privacy, allow the apps below to record the contents of your screen, even while using other apps. Meaning what? I'm not sure what this is.
Do you have a? So you don't have an option to share screen from the.
Let me just see what's happening here. I cannot quite figure it out yet.
Okay, sure. Also, Andrey, could you email me your slides? I can put them on the website.
Okay. Thank you very much again.
So this actually may be connected to the fact that I have logged in via my browser, because it seems that I cannot get my Adobe screen this way.
So there's no share screen option through the browser.
Let me just I have a lot of tabs open, so this is another. Let me try again. Share screen. Now I get just your screen, application window. Let's try something else. Let's try something else.
If that won't work, you can email me the slides, and then I'll. Well, you're just gonna scroll, which is
yeah,
not the best option, but
this may be better because I'm getting into some kind of labyrinth here of please grant browser access to screen recording. It's probably because you want to record that I get this problem. So let me quickly send
yeah, please email me your PDF
this file, because this may cost too much, and then I just ask you to go to the next.
Okay. Page. Okay, sure. Yeah, absolutely.
Yeah. Okay.
And maybe different countries have different restrictions.
Do we need to stop recording maybe to start sharing? No?
It's okay, because I should be fine. It should not be an issue.
Okay, let me see.
Did you send it?
One sec. Okay, I'm sending it now.
Got it.
You got it?
Yeah.
Okay.
Share the screen.
Wonderful.
Good.
Right. So, yeah, so I can start now.
Yes, please. Yeah, yes. Sorry for the delay. I'm not sure what was the problem. So our next speaker is Simon Ruijsenaars, and he will talk about Painleve-Calogero correspondence, the elliptic 8 coupling level.
Okay. Well, good evening to most of you. Good morning to some of you. This is about the connection between Painleve world and the Calogero world. And of course, this is well known at the level of differential equations. And the idea is here to see what happens at the level of difference equations. And in that regard, there were previous results by Kuchi Takamura. And this, however, is the highest level where you have the Sakai elliptic 8-parameter Painleve difference equation and Van Diejen's 8 coupling Hamiltonian. So this is as high as you can go in the hierarchy. Okay, the outline, yes, indeed, you guessed my thoughts. So a short introduction, then I will remind you of what Van Diejen's Hamiltonian looks like, and likewise Sakai's 8-parameter elliptic Painleve Lex equation. It's not the equation itself, it's the Lex equation that's connected. And well, then there are 2 steps to compare them. And that's the plan of the talk. So let's go to the introduction then. So at the ODE level, as I think probably all of you know, there are 6 Painleve type ODEs in a hierarchy. The most general one is mostly written in rational form, but it seems that even Painleve knew that you can, by a substitution, turn it into this elliptic form here. It got popularized in more recent times by Manin. But yeah, I've never actually looked at the reference, but I heard that actually Painleve has this somewhere in his work as well. Now, here is already something that's important to keep in mind. If you are at the level of ODEs, as you all know, you can freely change parameters. And so there are many, many different ways to write an ODE. Here there are 2 standard ways, just the rational form and the elliptic form, but you can make all sorts of other transformations, of course. And so it's a bit hard to recognize that you're dealing with a Painleve ODE because of this enormous freedom. Now, this is going to be very different at the level of the difference equation. And it is for that reason that it's only when you start from this elliptic form for this P6 equation that you get the link to the difference level, because at the difference level you can only write it in elliptic form. There's no way that you could get some kind of rational form. It would look absolutely horrible. So it's much more rigid at the difference level. That's another way of putting it. So yeah, we all know about the Ruijsenaars function, of course. Notice that the derivatives here with respect to the period ratio, right? It's tau that's being differentiated against. And the point is that this very highly nonlinear ODE can be gotten by means of a linear Lex pair formulation. And it is the linear Lex equation that can be tied in with the ODE that is usually called the Hoyne ODE. So that's on the next slide. Peter. Could go to the next slide, thanks. So here is the pertinent linear. Now it's linear, Lex ODE, and it's in Schrödinger form. And it looks a little awkward in the general case, but if you let lambda go to 0, which is of course a very special point, then these two terms drop out. And then you wind up with what is variously called the BC1 Calogero-Moser Hamiltonian, but also often the Inozemtsev one particle Hamiltonian, because Inozemtsev found an n-particle version of this Hamiltonian, where you have these external fields, these 4 external fields, but in addition a pair potential. Well, you have differences in sums of the coordinates. So it has then not 4 but 5 free couplings, because you can give that pair coupling another parameter. Right, so this Hoyle equation is really astonishing. It occurs in an enormous amount of context. There is in Sofia, they have a project, a Hoyle project, where there are hundreds, literally hundreds of papers that deal in some way or other with Hoyle equations. It's because they occur in so many different contexts. So it may be interesting for some of you who didn't know this yet to take a quick look there, the Hoyle project in Sofia. Yeah, so the corresponding difference equation can be called, because it's a difference equation. And the first time this came up in the setting was to bring in the speed of light. So this is then viewed as non-relativistic, and this extra parameter is the speed of light. So it's often also called the relativistic Hoyle equation. And that's then what we have at the difference level, and it has not 4 but 8 parameters. That's another thing that seems to happen all the time, that the number of couplings doubles as you go to the difference level. Right, so let's go there. Next slide. So Van Diejen has found this 8-coupling relativistic version, and Sakai, in a very different context, generalized the P6 ODE to, which has 4 couplings. Coupling type parameters is a better way to put it, because there are more parameters, of course. But Sakai has this geometric picture in terms of which you get at the very highest level an elliptic difference equation with 8 coupling type parameters. So this is on top of a huge number of coalescence and specialization limits, and the same is true for Van Diejen's Hamiltonian. Now, this is going to be joined with Nomi and Yamada. We worked this out a couple of years ago. We want to show, we were expecting, because of the previous results also by Takamura, and because of the fact that in both cases there is an E8 symmetry walking around, which I will very briefly mention in the next point. That was what sort of put us on the trace of expecting this. So the point is that in Sakai's setting, this while group of E8, or rather is a fine version, is sort of ingrained in it. It's the way that the equation is written via the translation part of this while group. Whereas for the Van Diejen Hamiltonian, it is really something quite astonishing, because these parameters are all on a different level, so to speak. There is an obvious D-H symmetry, but that there is also an EA spectral invariance is really very surprising. And more generally, this relation that we have found is really quite intriguing and very enigmatic, I would say. It is as if we have an answer to a problem and we don't know what the problem is. So what's the question that this gives a natural answer to? That is not clear. It turns out that they can be brought in contact, these two linear equations. So the linear Lax equation associated with Sakai and Van Dijen's Schrödinger type equation for his Hamiltonian. But as we will see in this talk, it is really something that's really enigmatic that you can do it in the first place. Okay, let's then start on this. So here is Van Dijen's Hamiltonian, not yet, because we need here first this absolutely crucial ingredient of the elliptic gamma function and the corresponding theta function. So here's the elliptic gamma function in the form I introduced it some, 24 years ago, or perhaps even longer, because I had it already in my Banff lectures of 94. Now, if you look at the two equations that it satisfies, because there's this A plus A minus symmetry, nowadays often called modular invariance, then the right-hand side of this ratio is the theta function that is here used. So I'm using a somewhat idiosyncratic notation here that dates back to this long JMP paper in which I introduced this elliptic gamma function. The point is that there are these two parameters, A plus and A minus, they're on the same footing. And as you know, with theta functions, there are so many different notations around that it would be very confusing to choose one of them and then give it yet another index, because there are naturally two of these theta functions around. So I decided to just use the right-hand side R plus and R minus functions for these two modular partners of analytic difference equations. So here it is, it's in terms of this infinite product, and it is just a renormalized theta function, okay? So actually, I have to click away something here. Please grant Brouwer access to screen recording, learn more, but then I get somewhere else, of course. I should have done this. I should have done this.
Or you just click it, right? I mean, the sharing goes from my computer anyway, right? So it shouldn't be a problem.
Okay, so you can record, Peter. It is possible to record.
We are being recorded right now, yes.
Okay, yes, because here there's this annoying thing that sort of obscures part of my view, that it says that, you know, I have to sort of give access, but you already have access, so good. So let's go to next slide then.
Sorry, just quick question about the previous slide. So you have R plus, and then you have x to minus x. Is just, you mean R plus minus, or?
No, I mean that the expression in brackets, they should replace x by minus x. So that becomes
multiply.
So multiply, it becomes just an even function, okay? I have that on the next slide, Peter. Next slide, Peter. Yeah, so it's obviously entire. It's even, it's pi on R periodic, has no real zeros, and that already tells you that it's really a theta function. So in this setting, you can write its analytic difference equation like this. Okay, this exponential pops out. Now in this form, then in this notational convention, Van Dijen's operator still has several different avatars. The simplest one is to start with this one. So again, this just means that wherever you see x, you replace it by minus x. The coefficient here is in terms of 8-fold product of these, these renormalized theta functions. So there are these 8 gamma mu's. They're like physical couplings. And then here you have, again, 8 theta functions, because of course you can expand these 2x theta functions in terms of 4 theta functions with x. So, but still, this is not itself elliptic unless there is a relation between the couplings. Okay, so there's a multiplier if you shift. It is periodic in the real direction, pi on r periodic, but not in the imaginary direction. You get a multiplier that only goes out if you have a linear relation on the couplings here. Whereas the additive part, these are the shift coefficients, the additive part is elliptic and even. It has these periods, and it has poles, simple poles, generically simple poles that occur at the zeros of this factor here. Okay, so this is 4 zeros, and then there is also the minus x. So it's the plus version and the minus version that you need to take into account. It's an even function. So in all, in a period parallelogram, you get generically 8 simple poles for this function here, but I'm not going to write it down. I will write down instead later on the residues at these poles, and that determines it up to a constant, okay, because of these ellipticity properties that I mentioned. Fair enough, let's go to the next slide. So there they are, these are the pole locations, and they of course are modulo the elliptic lambda lattice. So here are the residues. There are products over these 8 coupling type. Well, there are theta functions with couplings in as arguments, so there are 8 terms here. Mu runs from 0 to 7. And there's this overall factor which you find here, again, in terms of an infinite product. Fair enough, so let's go to the next slide. You can readily see that you have invariance of these residues under permutation and even sign flips, but one of them is actually not invariant under arbitrary sign flip. You get a sign there, so the sign flip, so it's not B8 invariant. The additive constant that I have not specified is to a large extent up for grabs. There is a natural choice, but I will not go into that because you can absorb it into the energy anyways when you look at the time-independent Schrödinger equation. Now, here's an important point. You can get rid of this coefficient of one of the shifts by a similarity transformation with a product of the elliptic gamma function. And that's another natural avatar of this operator A, so that's script A. And in this way, you see very clearly that this coefficient you now get, I didn't write it out, but if you do, then you can see clearly that it is invariant under even arbitrary sign flips. So it's actually B8 that you can put here for this part, but here we have this one residue that flips sign. So the whole thing is still in need of an even number of sign flips if you want it to be invariant. Now, this is also a form in which it is formally self-adjoint with respect to the Lebesgue measure. And well, from this point on, you may as well think of these 2 parameters, these modular parameters, as being positive, but you need not. The important part is that they are having a real part in the right half plane. Then all these products will converge because R is throughout, the real period is throughout considered to be positive. Okay. Now here's an important point. You can change the sign of the couplings in this product by having a similarity with a ratio of elliptic gamma functions, and that will be important to make this contact with the linear Lax equation associated to Sakai's Painleve equation. So that's why I'm making this point right here. You can flip the signs in this way. So that's something you can do still. You can still twiddle the signs around, and that of course doesn't change. None of these similarities changes the additive part. That's an important thing to realize, that it will not influence the additive part that's invariant under all these transformations. Right, let's go to the next slide then. So here we get...
sorry, I have a question. So the difference operator is this one, right? So it's script A plus acting on something equals 0.
Yeah, but it's just one of several versions of it, because depending on what purpose you use it for, you have several pros and cons for each of these versions. Here I'm just mainly mentioning it because this is the form in which you can use Lebesgue measure. Whereas for the previous original form, you would have to insert a weight function. Okay, so let's then now turn to the Painleve-Lax equation that Sakai has at the top of his hierarchy. That's where I switch to another convention for the elliptic gamma function that is nowadays far more widely used. Namely, you make a substitution. You make it's down here. You make an exponential substitution so that you just get everything in terms of this z parameter. And now the corresponding difference equation becomes a Q difference equation. So these are the two choices you have for difference equations, but this is all you can do. This is just no good analog of making a change of variables, which you can freely do in the differential equation context. So this is much more rigid. There are just these two forms, and there are analytic difference equations in the previous additive form that look very awkward in this Q form. You can make the substitution in some cases, and then you get something very awkward. So it's the additive form that's sort of the most general version for analytic difference equation, and that's why I personally always work in that particular setting. But there's a lot of work done in this Q setting, and that's what I want to share, want to sort of come to. So that's why we now switch to that. Okay, so in this setting, the building block, just like R plus was the building block in the previous setting, here it is this bracket Z function that is now the building block. And so here, another point is now that you single out one of these two P and Q parameters. Of course, there's still this PQ symmetry in the elliptic gamma function, but here we no longer make that distinction. We just use one of them, just like we used R plus in the previous context, but there is no further index to remind us of this particular choice. These are just conventions, but they're a bit confusing. That's why I'm spending a couple of words about them. So, okay, so this will be the key building block for the Lax equation associated to Sakai's elliptic Painleve equation. And here are the substitutions that you need. Right, let's go to the next slide, Peter. So here's the connection between these two building blocks, and that's what you need to do the calculations, okay? Now, what then is at stake? We want to compare the time-independent Schrödinger equation for Van Dijen's Hamiltonian to the Lax Q difference equation, which is of this general form. And again, there is one thing that already is very important to realize here, and that is that here you have much more rigidity than here, because this is just a difference equation. So you can multiply from the left by arbitrary. These are all meromorphic functions, an arbitrary meromorphic function on the left. That doesn't make that equation any different. Whereas here you cannot do that, because this form for the eigenvalue in this time-independent Schrödinger equation is rigid. You cannot multiply this freely by a function from the left, because then you don't have this eigenvalue here anymore. So that's important. This is much more rigid, and here we have the freedom to multiply from the left by an arbitrary meromorphic function. That will be important, because in this form, the way it's given here, it's not of this type. That will turn out to be not the case. So what we can do in both cases is make these similarity transformations. Here we can also make a similarity influence, transform these two coefficients. Now, because of the substitution that we made in the previous slide, it's clear how we should change between this function, this eigenfunction, as you would call it here, and this function y of z here. This is what you need. So that's the easy correspondence. That's what we should certainly do. And then the whole problem reduces to comparing these three coefficients to the coefficients of the difference operator in this A part, right? The constant is just going for the right. And that's why I also didn't bother to write down the natural choice for the additive constant in A+, because we have this constant here anyways. Okay, so that's what we're going to do now. So Peter, let's go to the next slide. The shift coefficients are of the following form. They are in terms of two products A and B that involve 4 couplings AJ and 4 couplings BJ. And then there is this script F function, which is just a product of 3 theta functions. And then there are these further theta functions that have a z squared, so that corresponds to the r plus 2x that we had. Okay, that's clear that that's going to be the same type of function. Now, what are these parameters? There is a parameter c here. That's just a gauge parameter. You can gauge it away. K is something that is a natural parameter in this extended affine E8 Weil group picture that is associated with the elliptic Sakai equation. There's no way I can even sketch the whole formalism of Sakai. That is just way beyond his talk. We were just taking this Lex equation from basically a paper by Yamada, but there are also other papers where these Lex equations occur. And we take for granted that this Lex pair gives rise to this Sakai equation, okay? And in that setting, this K is a very natural geometric parameter. Lambda is encoding one of the 2 initial values for this Sakai equation. Remember, we had also 2 initial equations for the P6 equation, the second order. Here, you also have 2 initial values, complex numbers, and at this stage, we only have this one. The other one is hidden in RZ, in the additive coefficient, but for now, I will not describe this additive coefficient. The only part of it that I can now more easily characterize is the function uz that features in RZ, which is the product of these A and B products. So we will look at RZ later on. So let's go to the next slide. First, we're going to compare the shift parts. And it's clear we have these 8 parameters gamma mu in the Van Dien context and the 8 parameters A and AJ, BJ in the Sakai context. And recall we have this gauge freedom in the shift coefficients, but not in the additive parts. And we can change the signs of the gamma mu, not in the additive part, however. So that already makes it very natural to make this relation between the two types of couplings. Here are the first 4 gammas, and here the next 4. Of course, there's permutation symmetry, so how you do this is not much. That's a matter of choice. What you get then is that this U of Z becomes something that we have seen already. Okay, so this is already the first hint that yes, we're going the right direction. So that's just one very tiny part of what's going on in all of the functions involved. So this is just a way to get started, so to speak. Now, what do you get with these choices? Here, I've written it down. And so that's what you get when you translate this now in terms of R plus. And this involves the log of K. Let's go to the next slide. If you choose K like this, then you see that the W plus and W minus coefficients in the Lex equation and the gauge transformed coefficients of the Van Diejen operator become equal. So this is where it's important to recall that this is something you can do. So there is this difference. It's not quite a permutation invariant as it stands in the Sakai context, but you can make it permutation invariant. That's another way of putting it. Well, we'll now use a convention that many of you will know already. It's just to shorten products that we will use this convention here. And then you can write this triple product of theta functions as this triple product of R plus functions. So here we use this convention, okay? Now, these we have seen in the denominators of these shift coefficients. So to get to the Lex equation, remember, these are just the factors, the A-parameter factors in these different coefficients that become equal, but that's not all of the coefficients. There's other stuff floating around. It's just the numerators where you have these A-parameter factors, okay? So that's why now we need to divide this Lex equation, the Sakai Lex equation, by that product. Remember, that's what I emphasized when we had this Lex equation, that you can multiply it from the left by an arbitrary function. That doesn't really change it. So going to the next slide. The result of doing that is that you get this form. This involves a bit of calculation, but you can somehow see that this must happen because we saw that on the previous slide you get something like that in the denominator, except you now must multiply by it. So this is what you're left with if you go through the motions. We still have this script f function sitting there, and there's an exponential that pops up. But we still have to parameterize lambda in some way so that we get a more natural form. And the first step to do so is that you write it as q times some new parameter nu and divide that shift part by this part. And that's when it gets into this form that now suggests what you should do next. Remember, this is going to be a little more general than the Van Diejen shift parts, because there's one more parameter, just like in the, remember in the P6 context, if you looked at a linear Lex equation, it has this extra parameter lambda that you had to put equal to 0 to get the Hoyne equation. So likewise here, we have this extra parameter, nu, that will make this deviate from the Van Diejen shift parts, and you will have to choose that parameter in a special way to reduce to the shift parts of the Van Diejen operator. So that's the plan on the next slide. Peter, we go to the next slide. So that's what we take into account by reparameterizing this this number nu in terms of a new coupling gamma 8, okay? Because then you get just a ratio of R plus theta functions where you have just this difference in how the signs appears. So they're ensuring that you get an evenness property. And the point is now that when you specialize gamma A to, say, gamma 7, you can also, of course, take any of the other gammas because there is permutation invariance in the other gammas. Then you get precisely the coefficients that we need, except that the gamma 7 needs to be shifted by A minus. So what do you get? You get up to these plane wave factors, because they're still there. There's also a factor Q. If you look at the previous slide, but let's not do it to save time. Here, you see that you have still this part. This is just referring to F, right? So we have this Q and this exponential still. But let's forge ahead. This is what we now have done to get to the gauge transform from Diejen operator, except that we have still the plane waves. Now, those you can get rid of by a further gauge transformation, and this is quite mysterious actually, because that involves the other theta function. We worked everything in terms of R plus. R plus was used all over the place, or the Z, the bracket Z function. But to get rid of that pesky plane wave, the only way to do it in a way that your transform function is having a real period, is pi on R periodic, is that you need a gauge function of this type, because then you get what you want. So it's this mystery here. Why does this work? Why is this the right thing to do? It's very tight. We could already have failed at several points in this procedure. So now, at least when we do this, we do get the same shift coefficients. Because when we go to the next slide, we, well, on the next slide, I already go to the acid test. But when we do it, I assure you that you do get the same coefficients, except for these sign flips in the 4 gammas, okay? But that's just a gauge transformation. So already that part, I emphasize, was very, very tight. It could have gone wrong at several points. But now we are still left with this additive coefficient. And now we have no choice left, because that is invariant under any of these gauge transformations. Remember, we have also multiplied from the left so that we got the shift coefficients in the right form. So we cannot no longer multiply from the left either. We now have to just go to this additive part and compare the two. And that's the acid test. It could still fail dramatically. But as we will see, actually, no, this becomes what we want. So this is the key question. And at this point, we then need to detail the additive coefficient of the Lex equation. So it's a sum of 3 terms. Here they are. S1, S2 are comparable. They're the same structure, whereas S3 on the next slide, Peter, is a bit different. It's down here, but let's first look at the S1 and S2. It involves a new ingredient, the script G function, product of 3 thetas. And there are 2 parameters here, but they're actually connected. And script L, or rather, how would you pronounce this? This is a calligraphic L or whatever, is again one of these natural geometric parameters that stem from the extended affine E8 Weil group picture of Sakai. And so there's a constraint between these two K and L parameters in terms of Q and the products of the complex. And so size is fixed in terms of that, in the sense that you can only choose one of the xi's and then the other one is fixed, okay? And you can view it as the second initial value for the Sakai equation. Now, what then is the third summand? That's the one that's a bit, what can I say? It looks rather inaccessible, because now what you need, and this is a new thing, you need actually you need evolved parameters, F bar, and where's the other? No, F bar, which was on a previous slide, product of three theta functions, remember. Let's not go there, because it's of the same type, but it has lambda instead of psi, and we went also to parameter k in defining it. So the only parameter whose evolution under the Sakai equation is very simple is k. So k, once evolved, at one step k is k divided by q, whereas c and lambda, you cannot readily write that down. It's very complicated actually, what c bar and lambda bar are. So as it will turn out, that plays no role in the end. And actually you can get rid of them. You can make everything completely explicit, which is another surprise. But that is something I can only come back to at the very end. So here is then the third summand. And now going to the next slide, we should first of all realize that this very inaccessible evolution is really completely fixed by requiring this. It's just, that these elliptic constraints cannot be made explicit. But this is what geometrically just means, that your R of Z has no poles at the zeros of G, Z that are manifestly present when you choose Z equal to Xi1 and Xi2. So that's really what fixes the evolution. Now, okay, so now everything is fixed. Everything is fixed now. So we have no choice, except if we still can reparameterize the xi's, right? And here we get two new parameters, but remember, these are connected. So there's really only one free parameter. And then lambda bar, we parameterize in terms of the same form that we had previously, but now with a gamma 8 bar. Now, if you now divide R of Z by all these reparameterized factors, then we have to, right? Remember, we needed these reparameterized factors to get the right shift bars. So R of Z was in the form that it appears in the papers that give you the Lex equation. And we have reparameterized R of Z, but we still have to multiply from the left by this bunch of reparameterized factors that we needed to get the shift bars be equal up to the gauge transformation. So there's a lot of work to do, so to speak, to get the final result. It's a long calculation, really long. But in the end, what you get is that your additive coefficient is a sum of three terms, here E of x plus E of minus x, and then an extra part that looks really awful, rather complicated. And E and VE are on the next slide. So here is the extra part, VE, E for extra. It has this evolved parameter and the evolved parameter gamma 8. And then in the in the denominator, you have this r depending on these two parameters phi of j. Likewise, here we have dependence on phi of j, these extra parameters, in the denominators of this function e of x. Now, it's not hard to see that these functions are all even and elliptic. It's straightforward. It's well, hard to see. It involves work, especially for e of x. Here it's not so hard, but here you have to do work. So you need paper and patience. So believe me, there are indeed also periodic in the imaginary direction, and you have to use the above relations to check it for this guy here. So it's not obvious, but it's not hard in the sense you have to just go through the motions to show that that's the case. Now, so then the sum of these three terms gives you an even elliptic function. By evenness, you do not get poles for this factor. That's a well-known thing. You can easily check it. That just follows from evenness, that you will not get poles at these 4 zeros in the period parallelogram. Now, what about the other poles? Because there are other poles now. Let's go to the next slide. Well, the point is, first of all, that you have this evolution requirement, and that means that you get vanishing pole residues, the sums, rather, of the pole residues at these zeros of the denominators will cancel because of this evolution requirement. And then you're left with still poles in z of x at these 8 points, and also at these points. But here comes the key point now, that when you take gamma 8 equal to gamma 7, then these poles drop out, and that entails that we're left with exactly the same pole locations as in Van Diejen's additive coefficient. So what we do now to compare the two is that we calculate the residues at these poles. And again, this is a rather gory manipulation where you need to use the relations between these various parameters. But lo and behold, they turn out to coincide with those of the Van Dijen additive part. So the upshot is that when you take the difference of Van Dijen's function, additive function, and the additive function in the reparameterized, renormalized Sakai linear Lex equation, then that difference must be just a constant. It cannot depend on x. So the acid test is passed. And what's more, I'll quickly add this, you can actually write this inaccessible looking function v e of x, which had these evolved parameters. You can actually rewrite it in a form that's completely explicit. That's in our paper. Maybe you can go to the next slide now, Peter, because that's where I have the references. So in our paper, there's an additional section where we actually rewrite this VE of x in a completely explicit form. And the upshot is that then you get two explicit forms for this additive coefficient that really look very, very different, because the energy, the eigenvalue is entering in the Sakai form in a very implicit way. It's just that you know that the difference is a constant. It cannot depend on x, but you have no idea where it sits, so to speak. So again, this whole thing, this whole correspondence is really, on one hand, very remarkable, but on the other hand, very unsatisfactory, because why is it true? So that's a good question to end this seminar. There's still work to do here. I mean, it really is the answer to a question. What is the right question from which it follows? There must be some better standpoint from which you can understand that this very intimate relation holds true. Okay, let me leave it at that.
Thank you very much.
Thank
Thanks a lot. Please, questions?
May I ask us one question? Maybe I don't understand some simple thing, but in non-relativistic case, we have quite simple picture. We have, for example, Lux pair for two-body Calogero-Moser model by Krichyver, and we know that it can be used, just the same Lux pair can be used to describe the Painleve equation by substituting this concrete Lux pair into zero curvature equation. My question is, can we do something similar by taking your Lux pair for two-body Ruijsenaars, elliptic Ruijsenaars model, or maybe a Lux pair by Cholich with 8 arbitrary couplings, and write down some kind of equation which provides discrete Painleve, Q Painleve. Can it be done?
Well, I think your question is very well put, and I must confess that I do not know whether there is a relation between this Lex pair formulation at the P6 level and the Lex pair formulation for Painleve for the Calogero-Moser elliptic, or rather the Diejen, the PC1 Calogero-Moser Lex pair that indeed, as you mentioned, can be found now in Shalikh's paper. Shalik has actually Lex pairs all the way up to the 8-parameter level, except that they are quite indirect. They have not been written down very explicitly. But your question is well put, and I don't know the answer to that. I think it's an interesting and challenging question to see whether possibly at that level there is also a relation between these two Lex pairs for the two settings. But it is not something that I can answer. I think it would be particularly important to make these results by Oleg Shalik more explicit, because although these Lex pairs are now there in this paper, they have not been actually made very explicit in the case of several external parameters. It's true not even for the trigonometric case. There you have 4 parameters. So for instance, think of SQ Wilson, right? There again, you know you can do it now, because in a beautiful paper of Oleg Shalik, you have a very general formalism that makes it possible to see that there is this Lex pair indeed, but again, there's still work to be done to make it explicit. And it's only when you make it completely explicit that you will be able to establish any relation to the Lex pairs that you have in the Painleve context, if there is any, because it's not a priori clear whether there is a relation. But again, I think your point is a challenging one. It would be.
But even if we discuss some simple particular case, I mean, not the Shalik case when all couplings are arbitrary, but maybe some particular case, for example, when all couplings are equal to each other, and in this way we reproduce just your two-body Ruijsenaars Lux pair. Can we use it to describe somehow discrete Painleve?
Yeah, again, that's a simpler question, and it may be amenable to an answer much more easily. But yeah, you just have to look at what these Lex pairs are in both contexts, and I certainly never looked at it from that point of view. But you're quite right. It would be a good idea to test this hunch that there might be a relation at lower levels in the hierarchy.
Okay, thank you very much.
Thank you. Any other questions? So I have a question about the symmetry. So you mentioned that there's a E8 symmetry going around, but could you maybe summarize how is it essential for the duality, for the Calogero Painleve duality? So, or is it not crucial here?
Well, it's really a different kind of symmetry. For the Sakai scheme, the Weil group symmetry is up front. Your equation is really the translation part of the Weil group. So there it is built in, so to speak. Whereas the surprise is that in the difference Schrödinger context, if you wish, the Van Dien context, you again have these 8 coupling parameters, but they certainly enter in a way that it looks totally non-symmetric when you look at an E8 transformation that's not a D8 transformation. For instance, you can choose your parameters such that you get really a free BC1 operator. You can make the coefficients equal to a constant. So then you have a very, very simple difference operator. But when you make an E8 transformation on that operator, you get something very complicated. So that the spectrum of that complicated operator is still the same as the one that you had, your free one, which you can write down because the eigenfunctions are they're just exponentials, basically, sine and cosine functions, if you wish. How is that possible? It looks almost like magic that they would have the same spectrum, and yet they do. This actually involves the kernel function that is used as a tool to make this connection between the spectra. So this is a very specific kernel function. In the next talk by Shlomo, I gather that he has several different ones, but you need a very specific one that has modular symmetry in particular to establish the relation of the spectrum of these difference operators to the spectrum of the Hilbert-Schmidt operator that corresponds to that kernel function. And this is the key point in proving that you actually have this spectral invariance floating around. But yeah, it involves a lot of work. It's in this last reference here, and yeah, it's a long paper. It's not something you can understand and explain very easily. It involves the spectral analysis of this Hilbert-Schmidt operator that corresponds to this kernel function. So the kernel function should somehow also be playing a role at the Painleve level. That's really what you might glean from this, that maybe there is a way to work into the Sakai context a notion of kernel functions that sort of might make it possible to make this link in a more natural, understandable way. But that's all I can say about it, Peter. It is really they're very different types of symmetry. Spectral invariance is quite different from the symmetry that is built into the Sakai framework, which the coalescence and specialization limits can all be explained in terms of degenerations of fine-cut-Moody algebras, as you undoubtedly know. So it's a very different way that the symmetry enters, and yet there are these very same Weil groups floating around. So like I said before, it's really enigmatic, and there's more to be learned here, I'm sure. But I have no further hunches as to in what direction that might go.
Great. Yeah. Thank you. Thanks a lot. Okay. In the interest of time, I think we should stop here. Let's thank Simon again. Now, I do think we need a 5-minute break, shall we? So let's start at 20 minutes past the hour with Shlomo's talk, and Shlomo will adjust the computer. So 20 minutes past the hour, whichever hour it is. So it's 11:20 on the West Coast.
Hi.
Oh, hi, Sergey. So Shlomo, I'm gonna make. You can share the screen now. Okay, great. Also, could you email me the PDFs? So I can upload?
Yes, I will email after the talk. After the talk is okay?
Yeah, sure, of course. Yeah, we can see the annotation. You will be competing with Thomas Dimitrescu's colloquium at 12.
Hi, Shlomo.
Hi, Simon.
And now I can see you. Yeah.
How are you?
Noticing that I have to click on something with Berkeley to allow this in the first place. Yeah, it's quite different from the Zooms that I'm used to here in Leeds. So that's why I also had trouble getting into this. I don't know what went wrong with.
I think you need to use the email account which is under your Zoom account. So it's like a security measure.
Yeah. I think there are also issues with versions. Like,
yeah, it also depends on whether you have a Mac or
possibly
or Windows or Linux. So yes, you cannot get a one-size-fits-all recipe for these things. That's why it is really good that you can quickly solve the problem by email.
Yes.
So Slava Spiridonov is in, right? Slava, you there?
Yeah. Yes, I'm here. Hello, everybody.
Hi.
It took almost 1 hour for me to join the meeting. I tried all kinds of tricks, and only when I created my own account into Zoom through Google account, then it let me in. Without that, it don't work at all.
I sympathize with that, Slava, because I also had trouble getting in.
Almost 1 hour.
With me, what worked in the end was that I had to click on the browser. I had to go into Zoom via my browser, which I never had to do before.
Very unusual. The first time I see such trouble. So at least now I am in Zoom account family by having a personal account there. Okay, I'm switching off not to take your time. Good luck with talk. I'm here.
Yeah.
Also, the topics of the talks, it was not planned, so that it's Van Diejen model. Yeah, so
but I'm very grateful for this scheduling opportunity. I will. Yeah, it's this model is very mysterious.
Yeah,
I don't know.
You'll tell us about string theory realization.
Well, string theory will be somewhere behind it, yes, but it's more too theoretical.
Okay, are you ready, Sergey? Perhaps?
Yes. Yeah, sure.
Great. So our next speaker is Shlomo Razamat from Technion at IS. He's now at a sabbatical. He'll be talking about 3 roads to the Van Diejen model and beyond.
Okay, thank you very much, Peter, for organizing this meeting and for giving me the opportunity to present this work. So, as I said, this will be very directly related to the previous talk of Simon, and it's great that I will be able to skip some of the parts rather quickly. And I will try to connect some things that Simon has mentioned. So this is based on a paper we're writing up together with Belal Nazar, who is a PhD student at the Technion, and Antony Delin, who is a postdoc, and he's moving to Geneva next year. And I will make certain connections between QFT computations and these integrable models. And the QFT part is heavily based on a paper we wrote together with Gabi Tzafrir and a couple of papers we wrote with Eviatar Sabag over the last couple of years. So Eviatar is another PhD student at the Technion, moving to Oxford for his postdoc next year. Okay, so as is well known, happy families are all alike, and today I will discuss two such happy families and connections between them, in particular what is similar between them. So we'll discuss a connection between six-dimensional quantum field theories, super conformal field theories, and elliptic integrable models. Okay, we will make a very explicit and particular connection between the two, and this connection will allow us to discuss certain very explicit mathematical properties of the Van Dien model that Simon has discussed in the previous talk. So the outline of my talk will be as follows. In part one, I will discuss the general logic of how one can obtain, starting from a 6D superconformal field theory, an analytic difference operator, okay, quantum mechanical, relativistic quantum mechanical system. Okay, so this part will be have a lot of physicsy jargon, so please bear with me and ask me any questions or anything which is not clear about this thing. Here I will discuss, the motivation of how we derive these models, what are the questions which we are interested in. And then I will use this general prescription in part two of the talk to derive from a very particular six-dimensional theory, the so-called rank 1 E-string theory, the BC1 Van Dien model that was the star of the previous talk. And in fact, we will have three different derivations of this model. So we will derive the same model, the BC1 Van Dien model, and we will call the different derivations by different names. So the first one we'll call A1 derivation, the second C1, and the third one A1 to the power 1. And the reason why, all these equivalent algebras, we split them in this way is that each one of them will have an obvious generalization. So there will be an AN generalization, and an integrable model will be which is a natural AN generalization of the Van Dien model, a CN, and a 1 to the N. And today I will only explicitly discuss the AN generalization. The other generalizations we actually did not work out. This is the work in progress part, but in principle, it's straightforward computation. Also, as Simon mentioned in his talk, there are, in this part of the work, the computations are clear. It's clear what to do, but they are very laborious and a lot of time and patience is required. And I will end with some comments. Okay, so let me start with part one, the relation between the analytic difference operators and 6D superconformal field theory. And again, please ask me questions at any point if you have them. So what is the general setup in which we are working? So what we are trying to do is to understand the dynamics of four-dimensional supersymmetric quantum field theories. Okay, so we have minimal supersymmetry in 4 dimensions. These types of theories exhibit a lot of very interesting strong coupling phenomena. And since these phenomena are strongly coupled, it's hard to understand them directly, like perturbative expansion fails. So one needs to find some alternative framework to discuss these types of models. And in recent years, such a framework has been discussed in great detail, where one embeds or engineers such 4-dimensional theory starting from a 6-dimensional theory. So the way one proceeds, one chooses a 6-dimensional SCFT. Okay, then one deforms this SCFT by some relevant deformation which is actually a geometry. Okay, so one puts this 6D SCFT on a compact Riemann surface and turns on some background fields for some global, some gauge fields, for example, for global symmetry of the 6D theory, which are basically the fluxes, and then flows to infrared. And effectively in the infrared, one obtains a 4-dimensional quantum field theory, which is labeled by this choice of geometry, which collectively I will denote by C. Then an interesting question is whether there is a weakly coupled theory defined in terms of fields and Lagrangians, which flows to the same fixed point. And this weakly coupled theory is directly in 4 dimensions. So if you wish, if such a theory is found, we have a duality between a 6-dimensional theory and a 4-dimensional theory. So here we have this geometric deformation, and here we have this more usual deformation using interactions and so on. Okay, so
are there any constraints on your curve C at the moment?
No, it can be, so it has arbitrary genus, and it can have punctures, it can have holes. We will discuss punctures in a moment. What kind of constraints you had in mind?
Whether, for example, it had a real structure. I mean,
it has.
I just wanted to know, could it, the moduli of it, right?
Yes, it has some complex structure moduli, so we don't constrain it. Like you just take any surface. In fact, the complex structure moduli of the surface translate into parameters of this 4D theory. Typically, they will become couplings of these 4D theories. Okay, so you take just anything you want, and you perform this compactification. Okay, so since this 4D theory, if we find it, is labeled by this geometry, a lot of non-perturbative, strongly coupled physics of this 4D theory is encoded in this geometry, and it is possible to extract it from geometric considerations. So a question which is driving this research is to find a dictionary between 6D theories, compactification geometries, and 4-dimensional Lagrangians. Okay, and then given the dictionary, try to understand the strong coupling dynamics of 4D CFT. So this is the background for this type of work. So, but here I want to not to discuss most generic facets of this work, but how this program is relating to elliptic integrable models. And the relation is through certain supersymmetric protected computations that one can perform. And in particular, we will discuss what is called the supersymmetric index of 4-dimensional theories. Okay, so given that we found this 4-dimensional quantum field theory, and which is labeled by geometry, and we can do several things with it. For example, one thing we can do is to compute various partition functions. Okay, and partition functions are typically take the form of counting certain protected operators in this quantum field theory. I will not go into details, but given such a theory, and the theory here I denote by T, it's labeled by the choice of the 6D SCFT and by the choice of the geometry. So collectively, I will label this choice by C. So we can compute this quantity that I will denote by this curly I, and it will depend on various parameters, which I will now describe. And we just compute some thermal partition function, some supersymmetric thermal partition function, because we have this -1 to the f. And this guy will depend on various parameters. Typically, we'll denote two of these parameters, Q and P. And these Q and P couple to geometric parameters in 4 dimensions. These are the Cartan generators of SU2 times SU2 isometry of S3. So this index can be also thought as partition function on S3 times S1. Okay, so these are the rotations of this S3. And R is what is called R symmetry in supersymmetric theories. Superconformal field theories always have an R symmetry. So we couple these Q's and P's to these charges. And then the 4D theory can have some global symmetries with charges Qi and the rank of, there might be some non-trivial rank of this symmetry group. If there are questions in the chat, are there questions in the chat? Okay. And we can turn on parameters for each additional parameters. The number of these parameters, it corresponds to the rank of the global symmetry group. Okay, so there is some function we can associate to this theory. So let me say a little bit more words about these parameters, as they will be important. So again, for generic n=1 superconformal theories, these indices depend on two parameters, P and Q, which will be exactly the same P and Q which appeared in Simon's talk. And then we will have these many parameters U, which depend on the flavor symmetry group. The number of these parameters depends on the details of the theory, how much global symmetry such a theory has. In our context, the global symmetry comes from two sources. So first of all, our six-dimensional theory might have some symmetry, which we'll denote by G6D. And depending on what type of fluxes we turn on, some subgroup of that symmetry is expected to be the symmetry of the 4D theory. Okay, and generically, we will not break the rank of the 6D theory. We will only break the global structure of this, like non-abelian structure of this group. So we'll have parameters associated to G6D. Moreover, it so happens that if we compactify our theory on a surface with punctures, each puncture comes with its own global symmetry. It is some computation that one can perform, and there is a whole industry of classifying various types of punctures and what symmetry one gets then one defines these punctures. This has to do something with 5D compactifications of these 6D theories. The details will be completely not important for us. The only thing I want you to know is that each puncture comes with a symmetry. There is a maximal symmetry that these punctures can have, and this maximal symmetry will denote by G5D. And then there is a variety of smaller symmetries which will not play a role except for the minimal possibility of a symmetry. And we will define a puncture which has this maximal symmetry, a maximal puncture, and the minimal, a puncture with minimal amount of symmetry, a minimal puncture. And the minimal amount of symmetry is typically either U1 or SU2. In our case, it will be always SU2 in the cases that we will discuss. Okay, so the parameters that the partition functions will have are these P and Qs, these internal parameters corresponding to the 6D symmetry, and parameters associated to the punctures, which in our cases will be some group G5D or SU2. And here is an example, not to be completely abstract. So if one starts with a 6D theory, which is called A1 2,0 theory, and compactifies it on a sphere with some value of flux in such a way that n=2 supersymmetry is preserved in 4 dimensions, and this sphere has 3 punctures, one can derive what is the theory, and the theory happens to be some collection of free superfields. One can compute the index of these free superfields, and it is given just by this product of elliptic gamma functions. And this elliptic gamma function Simon has defined in the previous talk. The G6D of this 2,0 theory in our notation is actually SU2. And G5D is also SU2. So this partition function depends on 2 types of parameters. It depends on this T, which can be thought of as a Cartan generator of this G6D, and also on a triplet of parameters X, Y, and Z, which can be thought as SU2 parameters associated to the various punctures of the surface. Okay? So this is a very well-known result in the physical literature. And much less known result is that if we take a different 6D theory, which is this rank 1 E-string theory, which is just another 6D SCFT, which has this nice property, the G6D, the 6-dimensional symmetry is actually E8, okay? And this E8 will be important in what follows. And the G5D is also SU2, as for the 2,0 theory. One derives that if one compactifies on a 3-puncture sphere with various types of punctures, very concrete types of punctures and very concrete value of flux, the theory that one gets in 4 dimensions is what is called in physics literature SU3 n=1 SQCD with NF = 6. And the index of this theory is this complicated function. So again, we have three parameters, this x plus, y plus, and z plus, which are SU2 parameters, which correspond to the punctures. And then we have an octet of parameters, okay? We have this u, v, w, and 5 parameters ai, which parameterize an SU6. And this octet of parameters is actually related to this symmetry E8 of the 6D theory. So it's a very well-defined function that we can compute. And from this function, we can derive various interesting properties. Any questions till now? Okay.
Sorry,
So,
just
yes.
simple question. The integral over dt, maybe that's what it comes from or signified.
Yes, so I didn't explain how to derive these things, from the field theoretic definition, but the way you obtain these things is that free fields, free chiral fields correspond to elliptic gamma functions. This has certain matter, certain collection of free fields. You write contribution of these free fields. This is the numerator here. And then you have a contribution from the vector multiplets that this theory has. And these integrals, they project on gauge invariant operators of this theory. So physically, the meaning of these integrals is projection on gauge invariant operators.
I see. So it's also, I mean, my obvious question is, like the Nekrasov partition functions, they made similarly, right? We multiply factors
yes.
from just the multiplets,
right.
But there's no integrations. And here we like the difference is that we have less supersymmetry.
Yes. So in relation to Nekrasov partition functions, well, I will mention in the end there should be a relation between what I'm saying and Nekrasov's Nekrasov partition functions, but here we have only n equal 1 supersymmetry in general. So the technology is n equal 1 supersymmetric. But once you go between dimensions, 4D, 5D, 6D, you mix between these various technologies, and eventually everything should be related. But,
yeah, it's interesting.
But we will not go there.
Okay, thank you.
So now with these indices, there are several things, generic things that we can say, and from which we will quickly derive these integrable models that I want to discuss. Okay, so in this geometric setup, when we build theories from 6 dimensions by compactifying on some Riemann surfaces, say we have understood what is the compactification of given 6D theory on some surface C with some value of flux. And we compute the index, and it is given here by some function. So this is the surface. And some other surface C prime with some other flux F prime. So here is this other surface. Then one can ask, what is the theory or the index of the theory, which is obtained by compactifying, by gluing these two surfaces together along some maximal puncture. Okay. And the answer is very simple. You just perform this integral. You take the contribution of the two pieces. There is a measure which is related to the gluing procedure, to the vector multiplets, and sometimes you need to add some extra fields, and you integrate over the symmetry of the maximal puncture. This is true for the index. For more complicated partition functions, that might not be true, but for the index, the supersymmetric index in 4 dimensions is very simple, and this is the procedure that you do to obtain indices of more complicated theories once you know indices of simple theories. Now, these indices are meromorphic functions of various parameters. In particular, they can have poles, and those poles, we can compute residues. And then you can ask the question mathematically, what is the meaning of these residues? And physically, like mathematically, what are these residues? And physically, what is the meaning of these residues? So the physical meaning that I will just very briefly mention is that if we have a pole in the index, since index counts certain operators, a pole actually corresponds to the possibility of turning on a vacuum expectation value of some operator. And the claim is that if we compute a residue at a certain pole of the index, one obtains the index of the IR conformal field theory, which is obtained by turning on these vacuum expectation values. So if we turn on vacuum expectation values, and in mathematically saying we compute a certain residue of the index in some U1 parameter, denoted here by U1, with this U star combination of other parameters, such that U star doesn't depend on these parameters P and Q, what we obtain is a certain quantum field theory in 4 dimensions, and we get an index of that dimension of that theory. If this parameter U star does depend on P and Q, since P and Q, by definition, they couple to this rotation symmetries on S3 in 4 dimensions, we break Lorentz symmetry explicitly. We give a VEV to an operator which is charged and which has Lorentz charges. So what we actually obtain in 4 dimensions computing these residues is an index of a theory of some theory which has a surface defect in it. So analytic residues of the index correspond in general to indices of theories which have surface defects in them. Okay, so this is the physical motivation to look at the residues. So now let us combine the previous 2 slides, and let us assume that somebody has told us what is the compactification of some 6D theory of 3 puncture sphere. And this 3 puncture sphere has 2 maximal punctures and 1 minimal puncture. Okay, so maximal punctures I will denote by circles, and minimal puncture by an X. Okay, now we compute an index of a generic theory where we glue to some theory this 3 punctured sphere. Okay, and then what we want to do, we want to find some natural poles in this minimal puncture parameter, which I denote here by a hat, and compute residues with respect to this guy. Okay, so again, mathematically, what we do, we just compute a residue. We give a VEV to some operator, we compute a residue, and we get an index of some theory in the infrared. If we did this computation with a constant VEV, no P and Q dependence, the theory that we get corresponds to the same surface which we had here, because this operation of giving a VEV simply removes this puncture from the surface, albeit the flux might be shifted. So the flux is given by the flux of this theory, the flux of this 3 puncture sphere, and also there is a certain prescription to assign a flux, which I denote A, to this closing puncture procedure. Okay. And finally, the final step in deriving these analytic difference operators from the index, say we can close the puncture in such a way that the shift of the flux, this A plus F tilde, here relative to the flux of the theory we glue to, is 0. Okay, and it's actually always possible to find such a theory if any 3 puncture sphere is known. Then if we just close with a constant VEV, we get exactly the same theory we started with. So this combination is 0, so we get exactly the same theory we started with. So this procedure of gluing a 3 puncture sphere and then computing a residue does nothing if you think of it as an operation on the index of this theory. So this corresponds to an identity operator, if you wish, acting on the index. However, if you turn on vacuum expectation values which are space-time dependent, or compute residues which depend on Q and P, what you find that this procedure actually gives you some non-trivial difference operator acting on the index of this theory. Okay, so this is the way the analytic difference operators arise in this construction by computing certain residues of poles of the index. Okay.
Sorry, can I have a simple question? Maybe I missed the difference between maximal and minimal punctures.
So the maximal punctures typically have some symmetry which can be big. Okay, some symmetry. The minimal puncture have a rank 1 symmetry, either U1 or SU2. Okay, and in what I will discuss soon, it will be SU2. And that means if we compute, say this symmetry is parameterized by this parameter ahead, single parameter ahead. So if we give a VEV to some operator charged under this symmetry, or mathematically we compute a residue for a pole in this parameter, the dependence on the symmetry of this puncture completely disappears. Okay, so it's as if we have wiped out this puncture from the surface.
But we were working with G5D also being SU2 in our examples.
That actually will be examples that we'll discuss in detail. There will be no difference between minimal and maximal punctures, and you can do that. But in general, this, say if this maximal puncture is SUN, if you compute a residue at one pole, you don't completely break this symmetry. You break this symmetry to a subgroup. Okay, so you are left with some puncture on the Riemann surface in this geometrical way of thinking. If the symmetry is rank 1, you erase the puncture. So that's the special thing about this minimal puncture. Is you go from minimal puncture to no puncture. Here you will go, if the symmetry is bigger than, has rank bigger than 1, you will go to some other type of puncture.
I see. Thank you.
Okay, so finally, there are the fact that these operators arise in this geometric construction. These operators have to satisfy certain properties. For example, this is related to the question I got about the complex structure moduli of the Riemann surfaces. So this, when we construct these theories from these 6 dimensions, we can understand first these basic building blocks, say 3 puncture spheres, and from them we can construct arbitrary Riemann surfaces, and the indices of these arbitrary Riemann surfaces are built by gluing procedures that I have discussed. And the point is that different ways to construct these Riemann surfaces correspond to different corners in the moduli space of complex structures of these Riemann surfaces. And physically, what this amounts to in 4 dimensions to some dualities of 4D theories. These indices that we compute, they are independent of continuous parameters. So it doesn't matter how we computed these indices, in which duality frame, we have to have the same result. So for example, we can construct the same Riemann surface where naturally, say some minimal puncture, it sits on together in a 3 puncture sphere with some maximal puncture or with some other maximal puncture. You should think of these theories as built from 3 puncture spheres. Then we perform this analysis of residues, and in this way we will obtain that this difference operator acts on this Z puncture. In this, it will act on this U puncture. So since the indices are independent of these details, these 2 things should be the same. Okay, so the difference operators acting on these indices should have these properties. And this is what is called kernel function property. We have a function which depends on Z and U. We have an operator acting on Z or operator acting on U, but the result has to be the same. So this follows from physics. Okay, and these 2 operators do not have to be the same. These punctures might be slightly different, and that will amount into some difference in these operators. Another thing which again follows from these geometric properties is, say, when we can consider computing residues in 2 parameters, it doesn't actually matter, following from these dualities, in which order we perform these operations. So using the operators we obtain, it doesn't matter in which order we act with them on the indices, we should get the same result. And since these indices are quite generic functions, these operators can be expected to commute, at least when we act on some very generic space of functions. Okay? So in this way, by understanding the analytic structure of the indices, we can derive a set of operators such that the kernel functions, the indices are the kernel functions of these operators, and that these operators commute. Okay, so the derivation of these indices, of these analytic difference operators, assumes that we understood this dictionary between 6D and 4D, and we can derive these operators. And then from the physics in 4 dimensions, we expect these operators to have these properties. Okay? The indices to be kernel functions and operators to commute. And what we are interested in is to check our physical conjectures about this dictionary between 6D and 4D, and checking these mathematical properties is a non-trivial way to do that for this particular dictionary. Okay, any questions about this part?
Yeah, a naive question. I'm just trying to understand how you are viewing your Z and U coordinates on this curve. if it's done intrinsically, I'm not sure what you're doing.
So these Z's and U's are, so these curves have some, you know, complex structure moduli, I don't know, metric, whatever. These Z's and U's that I define are unrelated to this. So this surface has a puncture, and to each puncture we associate a symmetry. And these parameters Z, U, A hat, B hat are the fugacities for these symmetries.
That's right, but where, I mean, is it independent of where these punctures are?
That's right, exactly. Because these are indices, and indices are independent of the continuous parameters of the theories. And the location on the Riemann surface is a parameter of this compactification, which translates into a parameter, into a coupling of 4D theories. The functions which we compute, the indices, are independent of those.
Okay, gotcha.
Okay, so this was very abstract physicsy discussion. So I hope you did not completely decouple. So now I will discuss several very concrete examples of applying this type of logic to derive the Van Diejen model. Okay. So to do that, we start from a 6D theory, which is called the rank 1 E-string theory. It's just some 6D SCFT that I already mentioned. And this 6D SCFT has an E8 global symmetry. And to punctures in this theory, we associate symmetry, which is SU2. And again, for this theory, the maximal and minimal punctures are the same. They're all SU2. It's either you have a puncture with SU2 symmetry or you don't have a puncture. Okay, this is one of the previous questions I have got. Okay, now there is a physical input to what I'm going to tell you. So for these particular compactifications, there are several conjectures of what four-dimensional theories look like when you compactify on three-punctured sphere. There are at least 3 such conjectures, and we will use very particular 3. These different conjectures differ by choices of details of the punctures. It's not that these conjectures are competing. It's just you understand 3 different compactifications, but they all correspond to three-punctured sphere, but differ by the value of flux or by details, finer details of what the punctures are. We can use any one of these 3 descriptions to derive these analytic difference operators. And in all these ways, we will derive a Van Diejen operator. Okay? And this Van Diejen operator will have the properties that the indices of these 3 punctured spheres should be the kernel functions for the Van Diejen operator. And these various operators we derive should commute with each other. And the commutativity of these operators will turn out to be a rather trivial property. And after we'll discuss this Van Diejen derivation of the Van Diejen operator, we'll generalize it slightly to something a bit novel. Okay, so let us do this computation. So this I already mentioned. If you take an E-string on a 3-punctured sphere, in one way of doing so, the theory in 4 dimensions is this SU3 and F equals 6 SQCD. And if you are familiar with the physics quiver notations, that's how you would write this theory. Okay? And this particular derivation of the Van Diejen model from this particular model, I will call the AN equals 1 derivation. So the index of this theory has this form. So again, we have 3 punctures which are SU2, which are parameterized by X, Y, and Z here. And we have 8 more parameters, which I denote by U, V, W, and this 5 parameters AJ, which actually parameterize SU6. Okay, so the symmetry that the physical theory has, in this way of looking at it, it has 3 factors of SU2, which again we associate with the punctures, and it has an SU6 times U1 cubed symmetry, which we think as a subgroup, which we think of as a subgroup of E8. So we compute this index. It depends on these parameters X, Y, and Z associated with the punctures, on octet of the parameters U, V, W, A, I, which I don't write explicitly, and of course on this Q and P, which are hidden in the definitions of these elliptic gamma functions. Okay. So now what we do, we feed this 3-punctured sphere into the machinery that we discussed in previous slides. Okay, so very explicitly what we do, we take these indices of 3-punctured sphere, which we denote by K k of x, y, and another parameter, z. And we take a generic theory with generic index, which we don't care what it is. We just denote it by IC as a function of T2, where T2 is a fugacity associated to the maximal puncture that this theory is assumed to have. So it's a generic theory, but we assume it to have at least one maximal puncture. And then we glue this 2-3 puncture sphere. So here is a bar over this index, and the bar means that we take this octet of parameters and conjugate them. So we take u to 1 over u, v to 1 over v, w to 1 over w, and this ai to 1 over ai. Okay? And in this way, if we have a flux f associated to this puncture, because of this conjugation, if you follow the physics of the arguments, the flux associated to this will be minus f. And if after we shift we compute the residues, the flux is shifted by a, here it will be shifted by minus a. So in total, the flux will not be shifted in this residue calculus, and then we will derive a difference operator. So given this function, we now compute two residues of this operator at some very particular poles, and we derive a difference operator acting on the index of this theory. So we can choose out of a natural set of operators to give a F to. These were these moment map operators, which I mentioned here. I don't go in detail, but for each such operator corresponds a pole in the index. And to be concrete, that is the residue that we are computing. So this is a very well-defined direct computation. It's very lengthy, but in principle, straightforward procedure. It requires to analyze various pinchings of integrals when you tune your parameters to take these values, and using various integral identities that were derived by some people in the audience, by Slava and by others, by Eric Reins and so on. And in the end of the day, this is operator that you get. It looks a little bit horrendous, but if you look closer, it is the operator which appeared in Simon's lecture, previous lecture. So it has, this operator acts on this function I of c, and it has this shift by q, a shift by q to the -1, and then a constant piece, okay? And the shift part, sorry, is multiplied by some factor, the same factor basically here, up to taking x to -1, and some constant function which is written here, okay? Now, you can go to the definition of the BC1 Van Dien model, and here is the definition of this model, which uses a notation of a paper of Eric Reins and Simon from 9 years ago. And you can just match the operator that we had on the previous slide to the Van Dien model. The Van Dien model depends on octet of parameters, and this octet of parameters can be mapped to this U, V, W, and AIs that we had in the physics C construction. And there is a map between these operators such that this term will match this term, and the another shift term will match this one, and that the constant term that appears here and is defined in a completely different way than on the previous slide can be shown to be exactly the same term that we have here up to a constant. Again, as in Simon's talk, what you do, if you prove that this function is an elliptic function, you look on its poles, and you show that the poles and residues of this function are exactly the same as poles and residues of this function. Okay, but there can be a difference in which is constant, x independent. So what we get to is that from this analysis of E string on a 3-puncture sphere and deriving this difference operator, the thing which introduces the surface defects into the index computation is this BC1 Van Dien operator. And the octet of operator of Van Dien is related to the octet of fugacities for symmetries that we have in this physics construction. Now, you can do this computation in various ways using the different poles. You will always get, turns out, Van Dien operator here up to some constant. So the difference will be only in this constant. So all these operators trivially commute. So the commutativity turns out to be trivial, but a non-trivial statement is that the kernel function, for this 1D operator, a kernel function is the index of a 3-punctured sphere, which we defined here. So this is a very particular integral expression, which depends on 3 parameters, x, y, and z, on which we can act with this operator, and it has this kernel property. This is what is expected from physics. We don't have a proof for it. So it will be very nice to have a proof.
So the cyclic symmetry is not manifest from the expression, right?
Which cyclic symmetry?
The XYZ.
XYZ, it's actually, there is no symmetry between XYZ.
I'm just reading the equation in orange, right? So the...
Yes.
Okay, it does not require cyclic symmetry. I'm sorry.
It doesn't require cyclic symmetry. And actually, these operators are not exactly the same. Okay, they are all Van-Dien, but they are slightly different because the definition, like the types of punctures that appear here are not exactly the same. I don't go into the details, but these are not, they are all of Van-Dien types, but the map to the Van-Dien between the parameters UVW and AIs to Van-Dien is slightly different for each one of them.
I guess it's probably maybe some residual symmetry from the assignment of those parameters, right? So like the SQCD versus the Van-Dien model, maybe that's what
let us discuss it after the talk, because it's a rich subject. Like, what is exactly the difference? It has to do with exactly how do you define these punctures. There is some freedom in defining them.
Sure.
Question.
Yes.
What about this K kernel function? Is it the elliptic geometric integral? So it's not the product of theta functions as usually people treat the kernel functions, but real
That's
integrals.
Right. It's just an integral. It's an integral of the type that you have discussed. It's just
which dimension? What's the dimension of the integral? It's 2-dimensional.
It's a 2-dimensional integral.
Okay, thanks.
Okay, so now let me make a comment about the E8 structure that you can see here. So as I mentioned, this SU6 times U1 cubed should be thought of as subgroup of E8, and the explicit way this SU6 U1 cubed is embedded in E8 is denoted here. And you can actually construct, by gluing these pieces together, these kernel functions, mathematically speaking, or indices of 3-punctured spheres together, to form a closed Riemann surface with 0 flux. You can construct an index of a theory which you expect has an E8 global symmetry. So this is
previous.
Yes.
As a previous slide.
Yes.
I'm a bit puzzled by the fact that the 8 parameters of Van Dien seem not to be on the same footing.
Excellent. They are not. They are not on the same footing. They appear very differently. You know, physics-wise, they appear as in this, like, like these 8 parameters, when you map, they correspond, 6 of them correspond to mesonic operators, and 2 of them correspond to some baryonic operators that you have. And this is related to the fact that you don't see E8 in this kernel function. You only see this SU6 times U1 cubed subgroup.
Yeah, the reason I find it puzzling is that you can write the Van Dien operators in such a way that the parameters are on the same footing. They are just manifestly invariant under all.
Right. So what happens here is that these operators differ from Van Dien by this constant piece. And this constant piece is rather ugly. It's not symmetric in these parameters. Okay.
So it's just in the constant that you get these different.
Exactly. So the shift parts are very symmetric. They are the same as in the Van Dien model.
Yeah, fair enough. Yes, that's why I was puzzled. But there's something else extra that breaks symmetry.
Right. So the non-trivial part of W is the same, the part which has poles, but there is a constant which depends on exactly definition of the punctures and so on, and it's rather ugly. And it's important for this kernel property. Without it, it will not work.
That's crazy. Really striking. Yeah.
Okay. So
I'm sorry.
Yes.
For previous slide. So I'm a little bit lost. So dx, dy, and dz, does they commute or?
Yes. Well, okay. dx and dy, they act on different types of, the dx acts on x, dy acts on y, and so on. And the way we define them, you can ask, okay, take this operator to act on x, then it's actually the same operator, and then it trivially commutes. You can construct other types of operators. So remember, we looked on a very particular residue, and that gave us an operator. We can look on another residue. We will get another operator. It so happens that in these constructions, these two operators will just differ by a constant term. So they will trivially commute.
Okay.
Okay. Okay. So again, let me just briefly mention that although the things seem not symmetric, there is only SU6 times U1 cubed symmetry. Once you glue things into these closed Riemann surfaces, basically you get rid of all the parameters corresponding to the punctures in certain ways. The integral that you obtain in this way should exhibit the action of the Weil group on this octet of parameters, the Weil group of E8. Okay, again, we don't have a proof of that. We have checked it in, computing these integrals and expanding them in Q and P and seeing that we see E8 appearing. But it would be nice to have a proof of E8, and that's probably related to other appearances of E8, which were observed many times in the past for the Van Dien model. Okay, so now very briefly, let me give you two other derivations of Van Dien model. And again, each one starts with a conjectured three-punctured sphere. So let me discuss the generalization, or derivation that we call C1. Here, the starting point is SU3 with NF equals 8 and some superpotential. It is also conjectured to be a three-punctured sphere of E string, but with other value of fluxes and other types of punctures. Again, we can define the index of this theory. It's a straightforward computation. We go through the same motions, through the same algorithm, compute residues, and again, derive a difference operator, which looks slightly different a priori from what we got before, but on closer inspection, it's again Van Dien model. Okay. Again, it just differs from Van Dien model by maybe a constant term. Okay. And again, the same statements hold. In any way we perform this computation, we get the same operator up to a constant term, so they all commute, and we have this new kernel functions, which are again a two-variable integral, but slightly different from what we had before, and it will be nice to have a proof. And finally, a final way I want to define this kernel function, it looks completely different. So in physics, yes.
Shlomo,
yes.
Can I ask about your parameters in this setting? Here you do have symmetry.
Here
it
is more symmetric, yes.
Because here,
yes,
they seem to be at the same footing in the second picture.
Right. So here the symmetry is a little bit misleading. So the symmetry that you start with is SU8 times U1. Okay, so it's more symmetric than the previous case. But then the symmetry is broken further by the choice of the poles that you look at. You see the poles depend, you pick one direction out of 8. And again, this enters through these constant terms also. So it turns out that the shift parts don't depend on this choice. It will actually, the generalization that we will discuss in the end will depend on this choice. But for Van Dien, it doesn't depend, but the constant part does depend on it.
Yeah. Okay. Same as before, actually. Yeah. Mm-hmm.
Okay. So the final thing, the final kernel function that I want to discuss is, again, there is yet another third three-punctured sphere, which looks completely different. It's built from two copies of SU2 and F equals 4. And in mathematical language, I think in the reviews that Slava has written, he calls the index of this block a V function. So you take two such V functions and some elliptic gamma functions, you multiply them together in certain way, you get an index which looks like that. Again, the two shadows of greens are just the two V functions, and these blues are just some elliptic gamma functions which don't depend on integration parameters. You obtain a certain kernel function, again, which depends on a triplet of variables. You go through the motions again, and yet again, you get a Van Dien operator, okay? Again, you have the shift parts and you have the constant part. The constant parts look differently than before, but again, you can, by computing residues, you can show that always the poles are the same, the residues are the same, but the different ways to derive it might be differing by a constant term. Yes, so again, this kernel function, this function that we defined also should have this kernel function property. We don't have a proof of it, and it will be nice to have a proof. How much time do I have, Peter?
No, 10 more minutes. Okay, actually you started at 50. Okay, so how much do you need? Do you need like 5?
10 minutes will be more than enough.
Okay.
Thank you. Okay. So summary of this part 2. So we have 3 different ways to obtain this BC1 Van Dien model by studying these compactifications of E-string theory. Actually, we have more, but the others are more complicated, turn out to be more complicated. And the reason I singled out these 3 ones is because they will have a natural generalization, as we will see. The first one we call the A1, the second we call the C1, and the third we call A1 to the 1. And they will have a natural generalization to AN, to CN, and to the A1 to the power of N type of constructions. Now, the fact that, you know, in all these different ways of computing, we get exactly the same operator is a consistency check on the procedure. It does, these operators, if you wish, they correspond to the punctures. It doesn't matter that we started from different spheres, okay? The operators corresponding to the puncture should be the same, and that's what we get. So it's a consistency check of the procedure. The factor that they commute is a check. A priori, you know, it seems a non-trivial check, but it turns out to be a rather trivial property of these operators that we get. And the kernel property of this indices is a non-trivial prediction of this procedure, which needs to be checked. If this is not true, something is bad with the physics, and the physics tells us that it probably should be correct. Now, I will mention this duality that Simon also has mentioned. I turned out vevs or poles which depended only on Q. There is nothing special in Q relative to P. We can compute the same operators, but exchanging Q and P. So we'll obtain Van Dien operators which just differ by exchanging Q and P. Okay, so this is another set of operators that we can obtain, and we can also obtain discuss residues in poles which have some higher powers of Q and P, not just Q and P, but say Q to some power and P to some power. And this will give us yet more operators. We did not compute these operators, but we expect in this case these other operators to be just polynomials of the basic Van Dien operator. But this is a thing to check. Okay, so now I go to the last part, the beyond part. Okay. So we discussed this, how to get this Van Dien operator from this special theory, the E-string theory. However, this E-string theory is just one theory in a sequence of theories, okay, which are labeled by some integer n. In particular, in M theory, in string theory, it doesn't matter. You can engineer these CFTs in 6 dimensions by taking a single M5 brane to probe what is called Dn+3 singularity. These 6D CFTs that you obtain in this way have a global symmetry, which is SO for n plus 12. So for n equal 1, you get the E-string that we have discussed. Naively, you have SO16, the D8 symmetry, which happens to enhance to E8. But for higher values of n, this enhancement, there is no enhancement, you get an SO for n plus 12 symmetries. These CFTs are usually called the minimal Dn+3 conformal method. It so happens that there are 3 types of maximal punctures for the generalizations. A maximal puncture with SUn plus 1 symmetry, USP to n symmetry, and SU2 to the power of n symmetry. For n equal 1, all of them are the same. All of them are basically SU2. And this corresponds to the 3 different ways that we looked at the Van Dien model. But once we discuss the generalization, we have 3 different ways to go. And we would obtain difference operators which act on SUn plus 1 types of parameters, USP to n types of parameters, or SU2 to the power n types of parameters. Okay? So the derivation is straightforward from what we have discussed, given that we have conjectured the three-punctured spheres, and we have them. And the computations are rather lengthy and complicated, so we only managed till now to do these computations for SUN+1, and that's what I will briefly tell you about now. Okay, so for SUN+1, the three-punctured sphere has the following form: is SUN+2 gauge theory with NF equals 2n+4 flavors. And the three-punctured sphere, which is known, has two maximal punctures of SUN+1 type and one minimal puncture of SU2 type. Unlike the Eastern case where everything was SU2, here we have SUN+1 and SU2. Okay, so we just repeat all the computations that we had before. We compute the index of the three-punctured sphere. It's just given by a multivariate integral here. Here we will have n+1 integrations. We have three parameters, two SUN+1 parameters and one SU2 parameter. So now not all of these three are on the same footing, only two are on the same footing. Again, we build a certain function, we compute certain residues, and we derive the difference operator. And the difference operator is rather ugly, and it is written here. Okay, so it has various shift parts. Okay, the shifts are defined here. And the shift parts come with some combinations of theta functions, some ugly combinations of theta functions. And there is a constant part, which is written here. And again, when n equals 1, you recover the Van Dien model. But when n is bigger than 1, you have this more general type of an operator. Okay. And what has to be the case is the following. Okay. So first of all, these operators depend, instead of 8 parameters, they depend on 2n+6 parameters, which can be identified with the Cartan of SO4n+12. One can repeat the computation of various poles and residues. And in this case, actually, one gets different operators for different types of residues, which are not just differing by a constant part. And all of these need to commute. And indeed, we have checked these operators do commute. So the commutation is rather non-trivial here. And the functions, the indices of three-punctured spheres that we have defined, these explicit expressions here, okay, they need to be kernel functions with respect to these ugly operators. Okay, and this we cannot prove, but this would be an interesting prediction of this type of an analysis. Okay. Okay. So are there questions about this? If not, I will summarize and make some comments.
I'm sorry, Kartanov, what orthogonal or number of parameters correspond to dimension of what Cartan group?
So the 6D theory that we start with has an SO4n+12 symmetry. Okay. So when computing indices, we can turn on parameters for the Cartan generators of this group. So we can turn on 2n+6 parameters. Okay. So the integrable model that we will build will have these parameters. For integrable models, you can think of them as the couplings of these analytic difference operators. For n equal 1, you will get 8 parameters. But this generalization has 2n+6.
Okay, thank you.
Okay, so let me make several comments. So first of all, as I already mentioned, there is a Cn generalization of this procedure, and there is a A1 to the n generalization. In principle, we can define these operators implicitly, but a computation is rather lengthy and we didn't do it yet. So this is a work in progress part. Moreover, this type of generalization, the A1 to the n, has a further generalization with one additional parameter, which I denote by k here. And in physics language, it would correspond to starting not with a minimal Dn+3 conformal matter, but with a non-minimal one. If you remember, the minimal is taking 1 and 5 brane probing Dn+3 singularity. So instead of 1, we can start with k and 5 branes probing Dn+3 singularity. And these groups are not just arbitrary groups. You can think of them as organized as corresponding to nodes of an affine D-type Dynkin diagram. And this has further generalization to AD groups. And the A part was also analyzed before, and it is related to some generalizations of Ruijsenaars Schneider model. Okay. Now, the important thing that I want to mention is that since these different types of punctures, they come from this for the same theory, we can have kernel functions which interpolate, I mean, they relate these different operators, like say the AN type of operators that we have discussed, and say these CN operators that we did not compute yet. For example, one such kernel functions for AN and CN, it takes this simple form. In physics language, is just simple Wezumino model. And in mathematical terms, it's just a product of elliptic gamma functions, no integrals involved. And if you put n equal 1 here, you will get a very well-known kernel function for the Van Dien model that Simon that appears in one of the papers of Simon from already many years ago. So this will be a generalization of that kernel function, but it will have an operator of SUN plus 1 type acting on it, and USP2N type acting on it. For n equal 1, this will be the same types of operators. Okay. So finally, let me sketch a rough map of these correspondences between various integrable models that you can get in this type of logic. And I got this question in the beginning, relation to the Nekrasov, the BPS-CFT correspondence, AGT, and whatnot. So the idea is that in recent years, there is an ongoing effort to classify the 6D CFTs. So there is a certain classification of 6D supersymmetric conformal field theories. You can think of this classification as following. You have a certain finite list of very simple superconformal field theories. Sometimes they call, or subsets of these are called minimal CFTs in 6D or non-Higgsable clusters. There are some fancy names. But there is a finite list of these CFTs, and then you can build sequences of theories which are labeled by some discrete parameters on top of these sequences. The A1 2,0 in this correspondence to integrable model is related to the A1 Ruijsenaars-Schneider model. And then this CFT has a generalization to AD type 2,0 theories, and then you can have AD types Ruijsenaars-Schneider models corresponding to that. And there are some other generalizations. The hero of this talk is the E string and its relation to the BC1 Van Dien model. And the rank 1 E string has a generalization to what is called rank n E string theory. The symmetry of this theory is E8 times SU2. This SU2 is not there only for the rank 1 case. So the natural conjecture is that this generalization would correspond to the BCN type Van Dien model, which has which has 9 parameters in general. Okay, and what we discuss here is yet another generalization of the E string theory to this minimal Dn+3 conformal method theories. And here we get these seemingly novel integrable models, although of course they might be related to things that people discussed in the literature before. And there are, for other theories appearing in this sequence, it's a mystery what would be the integrable models. For 2 of these, which are called SU3 and SO8 minimal CFTs, there is a suggested integrable models, and it was studied in these 2 papers. And what happens for others, it's not clear. So there is a question of what would be an integrable model corresponding to general 6D CFT. And it will be also interesting to relate everything we discussed more concretely to the BPS-CFT correspondence of Nekrasov. Now, I mentioned that what we are doing is n equal 1 supersymmetric, and all these computations heavily rely on having n equal 2 supersymmetry. So a priori, it is doomed. But if you look on the 6D origin, the 6D origin has 8 supercharges. So it's just when you compactify and using this geometry, you break supersymmetry down to 4 supercharges. But the starting point has an 8 supercharges. So n equal 2 supersymmetry, if you wish, is hiding behind the scenes. So probably there is a direct way to connect various ways integrable models appear in quantum field theory in this way. Okay, so there is a lot to be done, and let me just end with this question, very generic question, is can we map the classification of 6D SCFTs? And some related questions that I didn't mention of classifying 5D gauge theories which have a 6D UV completion. This is a very QFT-ish question to some sort of classification of elliptic integrable models. Okay, can we extract informations about the physics from the integrable models and about integrable models from the physics? I think it will be very interesting to understand. Thank you.
Great, thank you very much, Shlomo. It's a great talk. Are there any questions?
I had a question, maybe quickly. It's probably a simple one.
Yes.
So if you go back to the previous slide, yeah, the question. So in A1 to 0, the 2 n equals 2, right, case. So
yes.
if you think there is like the modular symmetry there is not straightforward. There is like some kind of modular or holomorphic anomaly there. And here
you're talking about compactification on a torus.
Yeah. You're not.
I'm not for everything I'm talking about is for genus higher than 1. Well,
you have the 6D, which you have a spatial toroid.
So the thing is like that. What we are talking about is take this 6D theory, compactify it on a torus, preserving certain amount of supersymmetry. Okay.
Yeah, but anomaly is actually in the UV parameter. Holomorphic anomaly, it's actually there is one in 6D, but there is also in 4D. There's if you write a UV complexified coupling constant tau for 4D theory,
right.
You have modular anomaly there.
That's right. So remember, everything I'm computing is independent of this tau. This tau is coupling. Mm-hmm. These indices are independent of this coupling. Okay.
Yes.
Okay, so that's very important. A comment is that you can do the things that I have talked about. You can discuss compactifications on a torus. A torus is a tricky surface. Many of these computations become singular on a torus. If you discuss torus with flux, with general value of flux, things become regular again. But, for example, if you compactify 2,0 on a torus, preserving n equals 4 supersymmetry, it's from this perspective is a very singular operation. So it's a side comment.
I see. Okay, thank you.
Now that you're on this slide, Shlomo, yes. What is E7 plus 1/2?
Okay, yes. So this is E7 plus 1/2 is not a group. In physics, it's E7. So these groups that appear here, so these are special theories, but the groups that appear here, they have the following physical meaning. So in 6 dimensions, the gauge theories are IR-free. Okay, so naively, you cannot get anything interesting by considering gauge theories. However, you can ask what happens if you go, instead of flowing to infrared, you go to UV. Okay, and then there is the following claim. If you take a pure SU3 gauge theory, no matter, just SU3 gauge theory with certain amount of supersymmetry, you get an interacting SCFT in the UV. The same for SO8, the same for F4, the same for E6 and E7 and E8. And with E7, you can do something else. You can not just turn on the E7 gauge fields, you can also add to it a hypermultiplet, a half hypermultiplet in 56-dimensional representation. And that theory is usually called E7 plus half. There is some mass origin of this, which is due to Delin, Tsvetanovich, and others, which noticed that this type of combination, there are some mysteries which happen with this sequence of groups, and there is a gap in this sequence of properties. Is formally, if you define a group which is E7 plus a half, which has this meaning, it is E7 with an additional representation, then it fills the gap. That's the meaning.
Okay.
A question?
One more question about the case where you have 2n plus 6 couplings.
Yes.
Is that so? That operator there, is that one of a commuting family of operators?
Yes, there are more. Yes. There are many operators. There are roughly 4n plus 12 that we found, times 2, where the times 2 comes from exchanging Q and P, which is simple. So it's at least 4n plus 12 operators. And naively, as far as we can see now, we're studying this in more detail, but they don't seem to differ just by a constant term. There is more significant difference between them.
Yeah, so it is also an integrable system, but of a new type.
It seems so.
Is it conjectural, or is it something that you can actually check in some way? Or
commutativity we can check. It's again, it's a lengthy computation, but we did, and they commute. These 4n plus 12 operators do commute.
Wow.
And you know, the same should happen for Cn. There should be operators which act on Cn. I don't know how they will look like, but I would expect the same number of operators. And for the A1 to the N. And I don't know if these are the only ones. I mentioned for Van Diejen that we computed residues which had single power of Q, and we got a Van Diejen. And if we compute residues with higher power of Q, I expect to get powers of this, or polynomials of the same Van Diejen operator. Here, I don't know what I will get. Here, maybe there will be new operators when you will compute these higher powers of Q, not just polynomials of this one. That actually, like, you know, the original computation we did is for this 2,0 theory, and there we get the Ruijsenaars-Schneider model. And there, that's exactly how it works. If you compute the simplest power of Q, you get the basic operator. And then if you compute the higher powers, you get other Hamiltonians. Until you hit certain power, and beyond that power, you just get polynomials of the things you already have obtained.
So it might be interesting to look at special cases where you, for instance, degenerate all the way to the rational level and take n equal to 2. So then you still have dependence on a lot of parameters, and it's quite intriguing what sort of operators you get.
Right, I don't know. We didn't study the generations. Yes, I don't know what you will get.
May I ask a question?
Yes.
Just a small comment. In 2004, there was a workshop in Kyoto. It was one of the first in the series of elliptic integrable systems, and Simon, I guess, was there. And in my talk, I claimed that elliptic geometric integrals the sources of a lot of new integrable models and body problems. And the reason for that was the following. I have found the first indications that these integrals emerge as eigenfunctions of these multiple integrable, many-body integrable systems. And that was my point of view on these things. And I am glad to see that I was right, although from a completely different point of view. Indices were not discovered at that time. Question is that the following about the wave functions. What can you say about the wave functions of these models? Because that was my idea, that using those integrals, I can get some eigenfunctions and from them discover the new models. And in your talk, you don't talk about it.
I have nothing to say except for, you know, naively, very naively, I would expect, say, if we have these eigenfunctions, that I would be able to expand them in some, you know, in terms of these eigenfunctions. But this is, I don't know to prove that, or if this sum makes sense, if it converges, doesn't converge, what will be the case. I have nothing to say.
So I see, you do not see the straightforward way to connect to eigenfunctions.
No, I suspect it, well, I don't know. I don't have something.
Okay, thank you.
But isn't it?
Yeah.
Oh, sorry, go ahead, Fabio.
Yeah, no, it's not me. It's
Yeah, go ahead, Gleb.
yeah, I just, is it in just to my mind it comes the comparison to Nekrasov partition functions and McDonald polynomials as wave functions. Like, but here K is not a partition function; it's an index. But can you think about this?
So McDonald polynomials appear in this, if you start from 2,0 in 6 dimensions. So let me go to this slide.
Yeah, they're wave functions. I'm just saying, like, in this language, maybe we have this comparison.
So there, when you start from 2,0, you get McDonald polynomials also in the index and in Nekrasov types of computation. And you
defects, right? You need to specialize in the
yes,
defect, and that's how you get it.
Right. I think the easiest way, I think, Peter, you worked on it, right? You go to 5D and you do this computation in 5D. So there is a certain relation.
That's right. So you get a wave function for the elliptic RAS model. Yeah.
Right.
So,
but I think, you know, with Van Dien, it will be very interesting to kind of connect. Again, the way we look at it, it's intrinsically unequal one supersymmetric. So there is no Nekrasov type of thing. But if you will go to 5D first again, you will get a 5D gauge theory, which has 8 supercharges. So enough supercharges to do Nekrasov type of magic.
Yes,
so,
it would be a good idea to just compute the defect, this
yes,
run
through the 5D
function, and see if it's the eigenfunction.
And see what you get and whether it's the same integrable model, another integrable, I don't know. You see, also here, you get different integrable models. For the same 6D CFT, there can be associated different looking integrable models. You have kernel functions which contain them. And, you know, for example, an interesting question is whether the fact that there are kernel functions, you know, for these different types of operators, does it mean that these two operators will have the same spectrum? Okay. These operators will act on different types of parameters, will look differently, but do they have the same spectrum, for example, or not? I don't know.
Well, it would be important to look at these kernel functions from the point of view of their Hilbert-Schmidt properties, because if you can show that, and it's likely true, then you can conclude a lot from that already, because then you get these eigenfunction expansions for free that just follows from general theory.
Right.
And that actually brings me to a question concerning the rank 1 case, where you have k, x, y, z. Is it true that x, y, and z are, is there permutation symmetry?
No, not really. Let me explain why. Let me go. It's if you will specialize parameters, you will be able to get permutation symmetry, but in general, there is no permutation symmetry. So if you look, like, it's easiest to explain in a physicsy way. Like, you look on these indices and you ask yourself, you know, you say you expand these indices in powers of q and p. So to lowest order in expansion, then you will get some non-trivial contributions. You will see that you will get something which will proportional, for example, to x plus x to the minus 1, okay, which is the fundamental representation of SU2, times these combinations of fugacities. For another parameters, which I denote here by y, you will get y plus y minus 1 times these types of combinations. And you can see they are not exactly the same. Okay, so there is a permutation if you also permute these internal symmetries.
Yeah.
So you act on this Cartan E8 in some way. But not just if you, it's like, so to be more precise, this k, x, y, and z depends also on this u, v, w, and ai. And it's not true that this is equal to k, y, x, z, but there is an equality if you will perform some permutation of the other parameters also. That would be the case.
Yeah. Well, again, if you would look at this from the point of view of the Hilbert-Schmidt properties by just fixing one of the 3 parameters, then this might tell you already a lot about what you can expect concerning spectra, because this is the idea that you use the simple spectral expansion for Hilbert-Schmidt operators to gain information about the very inaccessible spectral expansion for the different operators. That was the whole point of this long paper of mine. And this might apply also to this kernel function of 3 variables. We actually have something like that in my joint work with Martin Holness. From that point of view, you get what is called product functions. If you have such a kernel function from, you know, with 3 variables that are on the same footing, then you get what are called already since many years in mathematics product functions, where you can take products of eigenfunctions and that can be expanded in terms of the given eigenfunctions, and that's the way to look at this. It's a paper with Martin Holness that we fill this in, what I just said, for the case of the hyperbolic level and also the A level. It's really the A1 level where you have this structure coming in. Okay, so this is very reminiscent of it. That's why I'm bringing this up.
I see.
Oh yeah, it's very intriguing.
I see. By the way, I didn't mention it in the talk, but this kernel function, which depends on 3 parameters, it reduces if you compute a certain, take one of the parameters and compute a certain pole, you will get a kernel function with 2 parameters, which is exactly the kernel function you used with Eric Rines in your paper. So it's kind of, it's not, you know, it's just some generalization of that to 3 parameters, but it reduces to that.
Results already in a preprint.
Well, yes, if Anton and Bilal are in the audience, I hope soon. We are done with the computations and we are summarizing it. Yeah. But,
well, I'll keep an eye out for it.
Yeah.
Thank you.
Thank you.
Okay, more questions? Okay, I think we're getting tired. Yeah, it's, you know, almost for 4-hour session. Great. So let's thank all the speakers of the session, and then we'll meet again at 7 p.m. 7 p.m. Pacific time again for Gleb Aminov's talk. Great. See you later. Bye.
Bye.
Bye. Thank you.
Bye, Simon.